Okay, so welcome everybody. I'll go ahead and get started. Normally, if we were in person, this is the part where I would ask what everyone's favorite food is. Like if you go to a restaurant, what everyone's favorite restaurant is. It's fun in person because Austin has a lot of great restaurants here. The locals always have things that I've never heard of that are fun to go visit afterwards at some point. And people from out of town usually have something either they miss from home or that they're excited about. And I know for me, one of the places I love here in Austin is Ramen Tetsuya. So they have really good ramen. It's something that I cannot cook, but I really enjoy. I did see a YouTube video the other day on how to cook ramen, but I don't know that I have the skill set for it. And frankly, it's a good analogy for software containers. So today we're going to talk about a topic that we love. So the three of us that will be teaching are myself, I'm John, Eric will be teaching after me, and then this afternoon, Joe will lead us through some really cool hands-on examples of running parallel applications, GPU applications on a supercomputer. So all three of us really love this topic. We're always really excited to be able to share it with you. And essentially, this class is it's like delicious ramen. For scientific software, everyone who's doing research has some need to be able to run software. It's important. And it's the same way as it's all of us might enjoy our favorite food at some restaurant. We all want to be able to consume the thing that somebody else, some skilled craftsman has made. But that doesn't mean all of us can cook it. And in the same way, it doesn't mean that everyone who needs to use software is able to build software or write software. And so for a long time, software developers make code and then they just go publish how to install it and how to run it. And it's a bit like handing someone a recipe and saying, okay, these are all the ingredients. Here's all the bits of code you need to put in there, but you have to get them all working in one dish to be able to actually run the code and do the science. And software containers are a way to package all that up in one container. It's like takeout or scientific software. So today we're going to be looking at first understanding what containers are. How do we use other people's containers? We talk about containers as being a common currency now in research. So if people are doing research, if they're publishing software, a lot of the time, the best practice, I would argue, is to publish that software if possible as a container. And so that means the rest of us can use it if we know how to use containers and have that runtime installed. And it really is the simplest way in most cases. And then we'll also go, as the afternoon rolls on, we'll talk about building containers. This is like the expert chef's cooking a meal. We sort of have a responsibility in the research community to make software that is reproducible, that is able to be used by others. And knowing how to build a container and how to take some code that you wrote that runs on your laptop and package it up in a way that will run on everyone else's machine as well is really important and really valuable. And thankfully, it's becoming the norm. Okay, so with that, let me introduce you to what containers are. I'm going to click on the Introduction to Containers section if you're following along on your laptop. I'm going to leave this up here for a few minutes, and then I'm going to actually go to another tab and we'll use this as a terminal. So what are containers? Well, containers are typically compared to virtual machines. So maybe I should start there. Most people are familiar with a virtual machine. And inside of a virtual machine, you have one host computer that is the physical pieces, the processor and the memory and the board. And that would be the infrastructure. That's actually doing the computation whenever you want to run some computing task. And then for virtual machines, there's this layer called a hypervisor. And this hypervisor is sort of an interpreter. So inside the virtual machine, software will ask to be able to use to do some calculation. And then the hypervisor is an intermediate that then passes that request on to the hardware infrastructure. And VMs are great for what they're good at, but there's always a performance penalty of some sort whenever you have a hypervisor involved in the loop. And at a high performance computing center, we try and avoid those those flat off the top penalties to the performance that we're looking for inside of our apps. If you look at what goes into a virtual machine itself, it is essentially the app that you want to run. So whatever the piece of software is, along with all of its dependencies. But in addition to that, there's what's called a guest operating system. So that everything that the app wants to use, all the resources from the operating system that it wants to use, it will pull those from the guest operating system. And the guest operating system has to pass requests to the hypervisor to actually run anything. So it's sort of, it's like multiplying your computers, right? So you have these three completely separate environments. Separate is great, but it's the full stack from app all the way down to operating system. And then they only access the infrastructure through a hypervisor. So some technical terms there, but the difference here with containerized applications, if I can contrast it, is that first of all, there's no hypervisor layer. So the processes that run inside of a container are actually running on the host operating system. You can see there's no guest operating system either. There's no hypervisor, no guest operating system. Instead, what goes inside of a container is just the code itself and all of its dependencies. Now you'll see, and we've gotten questions before, you'll see as we go on that when we build a container, we talk about a base operating system. But when things are running, they are not running inside of a virtualized operating system. We just sort of use that Ubuntu container as a starting point because it contains a whole bunch of dependencies in that stack that our app can use. But when the process runs, it's really running on our infrastructure, and there's no performance penalty. You can look, or essentially no performance penalties. Sometimes there's a performance boost. There are a bunch of papers now talking about performance of apps inside and outside of containers. And the long and short of it is that containers are fantastic, even for apps that really need to extract every drop of performance from the hardware that they're running. So we end up with, when we containerize applications, as opposed to a virtual machine, is we have something that's smaller. Usually the size of the container is smaller than it would be if it were a virtual machine instead of a container. It's much faster to start up. So launching virtual machines can take seconds, and it's milliseconds to be able to start up a container. And then as far as passing these things around, Docker is this fantastic tool to be able to publish the apps up into a cloud space where they're accessible, and then to be able to run them on any other computer. There are some limitations, that might be worth mentioning, but maybe they're not. They're a bit far afield to talk about this early. Containers are compatible based on the instruction architecture of the chip. So if you're on this is a question will probably come up. If you're on a Mac that's ARM-based, and it's really set up to run ARM-based containers as opposed to the Intel x86 or AMD x86 chips, that is taken care of for Apple using an emulation layer, so it's not a big deal. But very occasionally we can run into edge cases where you need to sort of build the container from the Docker file for a specific architecture. And you can find those. You can find containers for specific architectures. But when we compare this to a virtual machine, the point is we have big advantages on performance, on the size of the container, and the time it takes to start up and run that container. That's the long and short of it. If we compare containers to just software themselves, which is sort of the other comparison to me, then what we get is software, raw code, will always have this set of dependencies, the various libraries and tools that the code is built on that need to be installed before you can run anything else, before you can install the software. And it's that set of dependencies that can really hold up science. Code these days, especially machine learning code, which we use a lot of here, it has a very deep stack of dependencies that make a lot of assumptions about the hardware underneath it. And we support those for sure outside of containers, but it's so much easier to support it inside of a container where you can package up all those dependencies inside. But it's not true that containers have no dependencies. The dependency is the container runtime. So you can only run containers if you have Docker installed on your laptop, on the machine you want to use, or another runtime that can support that type of containers, such as Apptainer. Okay, so there you have the comparison: containers versus VMs. Containers went out, especially for scientific software, for performance reasons. Containers versus just code running on a host system without any containerization. The container wins out on the dependency chain, that it's much simpler to be able to run that code. You don't have to install everything. And so it ends up being more portable and more reproducible in the context of scientific computing. So that's kind of the thrust of why we care about this so much. It's really good for science, for more and more people to be using containers to run other people's code, and also building containers to encapsulate their ideas and share them. So this morning we will be using a tool called Docker. We listed it in the class as a prerequisite to install Docker on your laptop. Hopefully you're able to do that. If not, you can still kind of watch what we're doing, but if you've installed it, you can follow along and be ready to go. This afternoon, when we start working on the high performance computing systems, we will use a different piece of software called Apptainer, also called Singularity is the old name for it. It went through a name change. But this we are using as a different runtime. So we will always be building and searching for containers using Docker. And then once we're ready to run the container, if we want to run it on an HPC system, we will use Apptainer. The reason that TACC installs Apptainer and it's training around it and really likes the piece of software is because it is a more secure environment for multi-user systems like high-performance computing systems that have thousands of users on them, to be able to run lots of containers without exposing any security issues or someone can try and escalate privileges. So that's the idea. Docker has some very well-known security goals. So it's great for your local laptop because you are the administrator anyway on your laptop. It's great for cloud instances where you're running a virtual machine where you are administrator, but on any HPC center, you almost certainly will not find Docker, not yet, because there are security issues. There are other resources. Docker Hub we'll look at here in a second. These are in Quay.io. These are places where you can find containers that other people have built. And I always like to highlight the biocontainers. I'll let you guys follow the link, but the biocontainers repository as well. It is a sort of a portal that passes you through to, at last check, it's around 15,000 different software apps in the life sciences space and bioinformatics space that are all containerized. So if you have, especially if you're doing genomics work, there are a whole lot of different tools you need to be able to run a workflow end to end. And you can do that all inside of containers for the most part. And it is very, very convenient. So it's out there in the scientific community. There's a lot of uptake. There has been for a couple of years now. It's pretty established. Okay, so as we get into it, let's see my turn now. Let me talk about a few words of jargon that we're going to end up throwing around. So if you're new to containers, you are probably, we're going to talk about a Docker file. And a Docker file, I think I have some, I'll show it in a second. But a Docker file is essentially the recipe, if we continue to adopt sort of the cooking analogy. In a way, this is the installation instructions. So if you ever tried to install in Linux a piece of software, usually there's an install page that says you download these libraries and do all these things. Well, that's actually captured inside of a Docker file to be able to package up all those dependencies. So a Docker file is a text document that is, maybe 100 lines or less of install instructions. An image, on the other hand, is the template of the container that contains all of this. So it's sort of the output. This is like your to-go box, or if you were ordering off the menu, this would be the entree that you order. It's the template that you expect to get once the food arrives. And so this contains all the code, all the dependencies, all the libraries, everything that the software needs to run. and it is packaged up. In Docker, it actually puts it in layers so that it can have some efficiency of not storing the whole file. In Singularity or Aptainer, it's just a file, but that file is the aggregate of all the compiled code and everything else. And then the container, this little piece, this is the same as the food that actually arrives at your door, right? It's not a template any longer. It is the actual food that you can eat. And a container is the actual code that you can run that is executing on your system. So this is sort of the instance of the image that's running, to borrow coding terms. So we can store Docker files in places like GitHub. We can share the recipes. You could pass them however you pass text files. That's fine. But then someone has to build the image using Docker. The other thing that we can share is the image registry. And Docker Hub is the one that we'll look at. Here, for example, is TACC's profile, Docker Hub. And if you look inside of here, we have all these different tools. Some of these are web tools that we use internally. Some of these are pieces of software that we support at TACC, like AlphaFold. This was Albert AI is a bot that plays the game Diplomacy for another project that we're doing. And so you can see there's just, if I go down, there's going to be many, many containers, pages and pages of them. But internally, we use this all the time, both for our own code development to be able to deploy it, as well as for apps that are user-facing that we intend other people to use. And it's not just TACC, right? You can search Docker Hub and you'll find a tremendous number of containers up here. So this image registry, you can use to essentially download the completely baked image that someone else has built and run it. And so there's a lot of security that an image will run. Again, we'll talk more about it later, but the big differences between a Docker file and image registry, it's the difference between sharing a recipe versus sending someone some food. If you just share the recipe, there's always the chance that someone will have a hard time finding the ingredients. So if something is built on a very old version of software, for example, you can share that in the Docker file, but it may not work anymore because that version has been retired. If you have already built the image, then inside the image, you already have the versions of the dependencies and things that you need. So they'll run. Gives you a bit more future proofing for over time if you share an image rather than just a Docker file. And then the way that we talk about images, it kind of has this syntax of something here, some word here, and a /, and then another identifier, and then a colon, and then finally this little version piece. So we talk about image tags, and that's what Docker uses to kind of define what these are. And there is an owner. So this, here is TACC as the example, or for my containers, it's usually whatever your Docker Hub name is, so John Fauner for me, or TACC, or whatever. And then inside here, this is usually the software. People use this for the software that they're talking about, the name of the container that they are building. And finally, this tag at the end is like a version. And by default, things usually get a latest tag, which is supposed to be a rolling update of whatever the latest one is. And hopefully people are also pushing version numbers of their code as well into version containers, so that if things change, you can lock what your workflow is to a version of the container and have consistency. Okay, so in summary, last little bit here, and then we'll go on and kind of look more hands-on, make sure everything's installed, and take a look at an example of a container. If you were the penguin here, there are a couple of things that you'll do. One is you can look at a Docker registry somewhere for existing images that other people have built. You can download those images and run them on any compute resource you want. When you download it, you're downloading the template, the image. When you run it, you're running the container. And the other thing that we can do is on our laptop, we can write our own Docker file. So if we are one of the chefs in the kitchen, if we are creating code, then we write our own Docker file. We build images from that, and we can run those ourselves or push them up to Docker. Hopefully that's clear. I will move forward to the next page, but this is a great opportunity to ask questions. If there's any questions you have on what a container is, what the advantages are, how it relates to software, virtual machines, anything like that, please post that in the Slack chat. I see chat messages coming through. Is there an automatic way to write the Docker file? It's the first question I see. I may be getting these out of order. There are really good resources for writing Docker files. If you follow along in this class, you'll actually write one. I don't know of tools that automate that process. To be fair, I mean, the technical answer is yes. So the way that biocontainers is built, it's using Conda as the build environment. So people post these Conda recipes, which is essentially a recipe for installing the software. And so they have tools to automatically translate that into a Docker file to containerize the app. So yes, you can automate it, but there's always a recipe. Someone has to write a recipe for how it gets installed. But yeah, Docker files aren't too bad. Another question, does an image include enough so that one can start with an image and modify it? Yes, you can. So you can take an image and then run a container. You can then modify that running instance of the container and save it as a new image. So that is supported in Docker. Yeah, you can also inspect the container to try and see what's inside of it. If you're on Docker Hub as well, a lot of the times you can get an idea of what the steps were to build the container. So it doesn't, I mean, I'll say it's when you don't start with a Docker file, but start with a container and try and modify it and save it, it ends up being hard to reproduce. So, right, it's like making a dish that you don't have a recipe for. It's like grandma's, famous, whatever they make, soup or macaroni and cheese or whatever. And no one else can do it the way grandma can because she's modifying things as they go. Their analogy means. Is the version control with image tags simply the organization of the images on Docker Hub? Or when you pull an image, do you also pull the different versions like cloning Git repository? Yes, so when you pull an image, you specify which version of the container you want to pull it. Let me go into one of these. So I don't know. I think a lot of these are only going to have one version. Here's TACC HPC. So if I look at the tags here, you'll see that there's a whole bunch of different things. So all these have the owner of TACC, TACC ML. And now if you look at this version tag, there's a whole bunch packed in here. For example, this is the version. Eric built these. So here, not only do we need like a 0.1, like semantic versioning, but we were really talking about, what's the base operating system, what version of CUDA is running for machine learning, what version of TensorFlow is running, and PyTorch and all that. So we could squash all of this into a tag. And so when you pull it, let me just copy it and I'll paste it. Paste it in this giant window. So you say Docker pull, and then it's TACC/TACC/ML. And then when you specify the version that you're looking for, the tag at the end, you put this whole thing in. And this gives you that specific version of all these things. This is a pretty involved example. I mean, right? So it could just be like a 0.1, 0.2 as the code is updated. But here people sort of branch into different things. If you look at Python, like if you download the base Python container, you see all the Python versions, and you see like a dev version of the container and all the different options as well. Okay. Oh, by the way, the last thing to say is these tags are generated by the author. So if you're the one building the code and pushing it up to Docker Hub, it's the burden is on you to correctly tag your images and do it in a coordinated way. So it's quite possible that I could go build an Ubuntu-based TACC ML image and then put this as the tag, and it will overwrite my wonderful image with one that is frankly deceptive. So the author is setting these up. Does a container have an address that you can access from across the internet? Can you SSH into, okay, let me start. Does a container have an address that you can access from across the internet? Only if you expose one. So there, probably half the websites you go to, actually that's an exaggeration, but probably 20–30% are containers that are hosting a service and you're accessing that service because they've made it available at a URL. That said, though, if you want to download images, these commands are reaching out onto the internet and grabbing this canonical location, this URL that's on Docker Hub to download the image. So in some ways, all of them do. The next question is, can you SSH into a container? Yes, we will do it. And the last one is, can you rsync files into a container? We will talk about file management a little bit later. So typically, you put containers either on a host or inside of a Docker volume, and then you mount that inside the container. So usually you don't need to put files into the container. You don't need to put files inside of a container. The container can just be configured to see the files that live on the host. Joe or Eric, did I miss any?
I think you got them all.
Okay, great. I'm going to continue on then. So this is the part where I highly, highly encourage you to play with this hands-on, especially if containers are new to you. If you are able to install tools on your laptop, there's a version of Docker that works well on Mac, Windows, and whatever your flavor of Linux is. You will know that your installation was successful when you can pull out a terminal and type Docker version and actually get something back. So I'm on a Windows machine currently. I am running Windows subsystem for Linux. So this is a Linux environment that I'm in, the Ubuntu 18 environment. And I have Docker installed. So I can type Docker version here. And I am at 2010.13. So hopefully you guys have that. If you don't, take time now while we're talking to go ahead and see if you can install it. If you have questions, reach out to us. This is the whole reason we have a Slack channel, is so that if you're stuck on something, we can help you with it. So the next little piece is a Docker Hub account. This will let you push images up that you create. We'll be doing that in this class. So you'll get to test that out if you have a Docker Hub account. If you need one, you can just go to Docker Hub and register for an account. Once you have it, we'll be using the command line to interact with Docker. So there's a Docker login command. I've already done it. But normally you'd enter your username and password, and it will log you in so that when you push images, it pushes them as you. And so kind of this last little thing that we want to do is look at some of the commands that we'll be using. So at the bottom of this page, there's going to be kind of this reference list of commands. They're really the core. There are other things you can do with Docker. There's a lot of different options, but Docker is a tool that's best to learn as you need it. So typically, if you're working with things, the first thing you'll do is log in. And then the next thing you'll do is Docker images. And this shows you what you have on your machine. So if you guys type the screen, you type Docker images, you guys may not have anything. You may just say a repository tag image I created the size. But over time, as you download images, you'll see these images appear in this list of things you currently have downloaded. And you can see, by the way, as far as sizes go, and this is something I want to talk about at some point, here's a big machine learning classifier with the database downloaded inside of it. So it's big. It's still 1.5 gigs, which is starting to approach the size of a virtual machine. But it's lighter weight than it would be if it were a virtual machine. For things that are small, where the code is not as big, you'll see these are down in the low megabyte range for how big they are. So there really is size savings, but these can add up. And we at TACC are able to fill up our hard drive sometimes with all of the Docker images that we're using and have to clean those up. But so these are the things that I have downloaded. If you guys are following along, then the way to get an image is to find one. So there is a hello world image that is part of the Docker official repository. So the tag for this image doesn't have an owner. It's just the name. And then there's some versions. So here's the latest version, for example, and there's some other tags of other options. So if I want to run this piece of code that was not developed by me, but developed by somebody else, then I can essentially download and install it all in one command. So here I say Docker pull. Pull is the command to go out to either Quay.io or the hub or somewhere and bring the image down. And here, the default location for these is Docker Hub. So that here I can just put the name and tag. So hello world. Normally I would put a colon and then the version number, but by default, latest is the default version. So here I can use the maximum shorthand and just say Docker pull hello world. And it says using the default tag latest. And it will go ahead and pull it down. I already have it here, so it's going to be fast. The image is up to date. So now if I want to run this, the command is Docker run. And this will run, we'll talk more about this, but just to introduce the concept, there's a default command or default entry point that's associated with a container. And so when you run the container without any arguments, it will just run whatever the default command is that the author has set up. So I say Docker run hello world, and by default it prints some very kind output. If you run Docker images again, here you won't see much different because I already have it. But if you guys run it on your local laptop, you'll see that now you have hello world. And then the last thing, if I have a container running, there's a Docker PS command. Right now, nothing is running. My containers are stopped or closed. This will give you a list of things that are running. So we don't need this right now, but just know that it's out there. Docker images gives you a way to see the images that are on your machine, the templates that you can use, the menu, if you will. And Docker PS tells you what you're actually running. Okay, we can do Docker inspect. Tab works, by the way. As I was typing Docker inspect and I started to type a container, I can press tab and it will autocomplete, which is quite convenient. But we're talking about, what all is in a container. And there's quite a bit of information about what has gone into the container. You can pull some of this with the inspect tag. There's not a whole lot that I want to do. We talk about a default command. This is the default command that it's running. It's running a shell with this command inside of it. So again, just good to know that's there. Okay, so the flow that we'll have, and then I'll give one more example that I'm going to hand over to Eric. We are on pace, I think. So the flow is we'll log into Docker Hub. You find something that you want to be able to run if we're using other people's images and not building them ourselves. And then we'll pull these down using Docker pull. We can double check that they're there with Docker images. And then we're going to maybe inspect them if we want, but ultimately we're going to run them using the Docker run command with some arguments to it. The rest of these that are going on are things to manage containers once you have them. So if you have a Docker image you don't want anymore, you can say Docker RMI to remove the image. Or if you have a running container that you need to get rid of, Docker RM. If you're familiar with Linux, you'll notice RM is like the same as to delete a file, the same command to delete something. Docker stop is just to manage running images. And then these last three, logically, are when we're building things. So if we're building our own code, then we would ultimately use the command Docker build to turn our code and the Docker file into an image. We can then put a tag on that image and push it up to Docker. So if you reference this list, it's kind of broken out that way logically. Finding things, pulling them down and running them, cleaning up after you run things that you don't want there anymore, and also building things. Okay, so the next section is one that I'm not going to go over specifically. There's a fair bit of duplication in what Eric is going to talk about when we start building images and what I would talk about here. So it's left there working with Docker. You can reference that material anytime you want on read the docs, but I'm not going to go over it directly. Instead, I want to go over an example, and I'm going to go in this window. Instead, I want to go over an example of a container that, what's going on? A container that I made that to run an image classifier. And the idea is that you guys could, I can share this with you, you can run it. You can also kind of see what went into making it. So you've probably heard of ResNet. It is an image classifier. So you can give it, for example, a picture of a lion or a picture of whatever you want. And that's the input. And then as output, it gives you predictions of what it thinks the contents of that image contain. It's always a fun little tool. I mean, it's a great research tool. But one of the things we can do is just take a kind of a simplified version of the database, and you can run it on your laptop or run it anywhere for fun, which is what I've done here. So I wrote a very short a very short Python script that uses TensorFlow to load ResNet 50. I think half of these lines of code are something I just got off the internet, right? Of someone who has an example of executing ResNet. I added a couple of options. Those that are familiar with Python, this might mean something to you. If you're not, don't worry about it. And that's it. So this is 43 lines of code. From there, though, if I want to be able to share it with someone, I made a Docker file. And this Docker file is only 14 lines of code. And so what I did was I started with a base image that already has most of the dependencies that I need, so that I don't need to install much. I installed the rest of the dependencies. Again, if you don't know what this means, that's okay. I mean, this is like cooking. Here I was the chef. I knew the ingredients that went in here. I think one of you is really good at making chili. You know, you've got your recipe for chili. So I knew what I wanted to put in here, and I added it. I added my image classifier inside of the container and made it an executable. I downloaded the weights, the ResNet 50 weights off the internet, and put that in the container. It's one of the reasons why this container is so big. And then I had to do a couple of other things. I had to update a path environment. I had to throw in an environment variable. And then I made a default command. So once I had done that, I used Docker build, the Docker build command. I gave it a tag. And then I told it to build this directory. And when I was done, I ended up with, I think it's off the edge of the screen. Here it is. I ended up with an image that I can run, or that anyone else could run. I called it ResNet 50 classifier. Not a great name. Well, it's descriptive enough, I guess. And I tested it, and then I pushed it to Docker Hub, so it's up there. So now any of us can run this container. Look, it doesn't do much, but it's a toy example. And to run it, we would say Docker run, and we need to give it a few flags that we haven't talked about, but just to show them. Make this a little bit bigger. Yep. And I will clear. There are some of the distractions. So it's Docker run --rm says that I don't want to keep the instance of the container once I'm done. And then I need to mount some. I need to mount some data image. I need to mount a directory inside the container. This goes back to one of the questions from before. So there's a -V flag which says volume mount. And in this case, I want to take my working directory from right here. Does TensorFlow image have the Ubuntu base image in it? I actually don't know. I actually don't know which one this is built off of, but we could go to Docker Hub and look. Right. So we take the current working directory on the host machine, and I will mount it inside of a directory that I call /data inside the container. Then I will run John Fauner, what do we call it? ResNet 50 image classifier. I think I give it version 0.1. And if I just run this, then I will get the default output. Oh, here's actually nothing. It's supposed to be the help text. I'll just get the default output of the container. But it's best to go ahead and put the command that I want to run inside there. So I want to run image dash classifier. See where I make a mistake. Hi. So here should be the help text. So these are the options that I can give it. I'm just pressing up to repeat the command. And so here I want to specify the image. So I'll use this lion.jpg image. But inside the container, right, I've taken this directory and I've stored it as /data. So I'll say my image is /data/lion.jpg. We'll go from there. So this is going to give me all the output as if I were running this without the container, right? It's going to give me standard out, standard error. So it's going to give me these little memory warnings as I'm running it, because that's part of what standard error would be, and kind of the progress stuff that it's doing. And then finally at the end, this is my output. And actually, if I go into the code itself, you will see that I want to print predicted, the colon, and then I want to take my predictions and spit them out as Python tuples. So here's my predicted colon, and then inside here are the top three predictions that it made. And the one it really thinks it is, with the weighting of like 99, the confidence of 0.997, is a lion. And if it's wrong about that, maybe there's a small chance this is a lynx or a dole or whatever that animal is. So there we got to see it in action. This is, I don't have TensorFlow running on my laptop. I don't have any of this. In fact, VS Code tells me that I don't have any of this because I'm developing on my Linux environment, and it's giving me flags everywhere because I don't have any of these libraries installed. They only exist in the container. I could package this into the container and then run it. So there's an example of taking something I wanted to do, ResNet, pulling it down. Here I had to write it because I wanted to define the interface, but for you guys, you can pull it down off the internet, off of Docker Hub. You can inspect it, you can run it, and get all the benefits of having that software without really any extra steps of doing the installation. Okay, that's it for me. I was shooting for about 45 minutes. It's about 47 minutes. This is a good time if you would like to stand up, stretch. Please ask questions in the Slack channel or the chat. Eric or Joe, is there anything I should mention before I hand over the control to you, Eric? How do I test this execution on other flavors of Linux? The thing is, it doesn't matter what flavor of Linux I use. So you can run this on Mac. Here I'm running it inside of Ubuntu 18, but if I go inside the image, it's not necessarily going to be Ubuntu 18. I think that's a demo that Eric will show in the next section. So the flavor of Linux that I'm running it in is the one that's specified in the Docker file. So anything that can run this Docker file can handle it. This is definitely the beauty of how this works. Any other questions? That looks like everything. So with that, I'm going to mute myself. I'm going to hand over to Eric.
There's a question in the Slack.
Okay. Can someone read that? Oh, this is I use Podman because I'm a Fedora Linux user. Both Podman and Docker are available. Yep. Any huge differences between Docker and Podman in terms of programming environment? Seems the syntax is the same. Yes. So Podman is compatible with Docker. So Singularity also has its own flavor of file. So instead of Docker files, it has Singularity files that give the recipe. We tend to just stick with the Docker ecosystem and just use that because everything else has to be able to import Docker containers. So it's very convenient. So Podman is great. All right, and how do you test it? Oh no, I did that. Okay, I think that's everything. All right, I'm going to quit talking, hand this over. Thanks for your attention, your good questions as well. I hope this is helpful. And please stay. I mean, the next two sections are great. The next one is hands-on on a laptop, no more hand waving or talking about things we aren't actually doing. And then the other one this afternoon is actually on TACC systems, which is if you're going to use any academic cluster, it's a great example. All right. Thank you very much.
All right, I will share my screen. All right, can everybody see that? How's that look in terms of size, font size on the?
Yeah, that's fine. We can see it.
Okay, great. Well, thanks everyone for sticking around to section 2. My name is Eric. I've been at TACC for quite a while, and I've been using containers for quite a while. So as John mentioned in the intro, we're all pretty excited about using containers. And in this section, we're going to kind of talk about how you as a researcher who's developed a new application, a new algorithm, a new piece of code, will want to containerize that and distribute it and share it to colleagues and other end users. So what we're going to do, really the only prerequisite for this section is having Docker installed, which John covered a bit in the beginning. So one of the things we're going to do is we're gonna kind of build up a typical developer workflow. You've built a tool, built an application, and you're going to want to kind of decide on what OS you're going to use to build it in, what tools you're going to need, what dependencies you need, and we're going to kind of massage that into a container. And the beauty of that is that if you've ever gone to kind of GitHub or anywhere to look at an application or a tool, and if it's well written, they'll probably have a README that describes kind of where it was tested, the OS it was running under, what system packages or dependencies it needs. If it's a Python script, what Python modules it uses. So what we're going to do is kind of bake that all into a container. So when it comes to the end user using it, they don't have to worry about that at all. That's all built into the container. So the first thing we're going to do is we are going to make a new directory for our application. Now, one of the reasons we want to do this is that Docker, specifically the Docker daemon, when it runs, uses a concept called a build context. So I'm sitting here. If you look at the terminal on the right, you'll see that I'm actually on a Linux VM, and in my home directory, and you can see that lots of directories and files. So if I were to start putting my files in here and my Docker file in here, the build context would be everything in the current directory and underneath that. So that's not really efficient. And if you were building things over and over again, you don't really want to do that. So what we want to do is narrow that build context down. So what we're going to actually do is make a directory. I'm going to call it Python container. You can call it whatever you like. Okay. So now I'm inside the directory. What we're gonna need eventually is a Docker file. So I'm gonna touch that, and we're gonna come back to that later. So we're in our Python container directory. We've got it, and we've got our Docker file. So now let's grab the code we want to containerize. So this is a fairly simple Python-based Monte Carlo simulation of how to calculate pi. Basically, the algorithm basically works, but it draws a unit square. It has a square, and then inscribed inside that square is a circle, and it basically will drop random points, and if they end up inside the circle or outside the circle, so the ratio, 4 times the ratio of that, the number of tries versus the number of attempts will give you kind of an estimate for pi. And as a standard with a Monte Carlo simulation, the more points you have, the better your estimate's going to be. So you can either cut and paste this code if you want, or you can kind of use wget, which I'm going to do to pull it into my directory. So now I'm in my directory, and I've got my Docker file, and I've got my pi.py file. So so as I briefly mentioned in the beginning, what are the kind of considerations that I have to think about when I am going to build my container? So the first thing we talked, and John mentioned this a little bit, his intro was what's an appropriate base image, or what OS am I going to base my image off of? In this case, I'm going to use Ubuntu 18, as you'll see in a little bit. It really depends on what your development environment is, what you're comfortable in. If you're more comfortable in CentOS, that's fine. If that's what you're targeting, that's fine. You're more used to building and pulling dependencies, but that's fine too. So in this case, we're going to use Ubuntu 18. The second thing you're going to have to think about is, what are the dependencies that are required for my program? Like I said at the beginning, what system dependencies, what packages? If it's Python, what version of Python do I need? That's kind of the second thing you need to think about. The third thing you need to think about is, is there any kind of install process for my program? In this case, it's just a Python script, so it's pretty simple. But you could have a tool that a C or C++ tool that you need to build. Maybe you have a make file. Maybe it's a package from a package manager to install. So there's various ways that you can install things. So you got to think ahead of time. How is the tool or the program you're gonna build and how's it built? And a fourth consideration is what's the environment that the tool is going to run in? What does it need? Are there any environment variables that might need to be run? So we would consider that as well. So once you've done this a while, you probably will immediately start hopping into a Docker file and writing it out. But when you're first starting out, and even if I have like a complex install, I like to kind of do this what I would call interactively. So we're going to kind of work through those 4 questions in kind of an interactive session, and build up this install and test it out, to kind of test out how we would install this. So as John showed you a little bit in the first section on how to run a container, we're gonna run a bare Ubuntu 18.04 container, and we're gonna actually shell into it, and we're gonna work this interactively. So I'm gonna go type docker run -it. Now IT is what allows you to interactively attaches a terminal to this container, so you can kind of shell into it. The next thing I'm going to do is I'm going to bind mount my current directory, which contains the Docker file and the pi.py file, into the container at a directory called /code. Then I'm going to specify the Ubuntu container and version, and then I'm going to specify the command to run when I run this container. I'm just going to run a bash shell. Now, if you don't already have that Ubuntu container locally, it's gonna go pull it, which you can see it here. Now we have the new image, and you can see the terminal has changed. Now we're actually sitting inside the container as the root user. So basically, right now it looks like I'm inside an Ubuntu machine. So the first thing we're going to do, what's the first thing you would typically do if you had a fresh Ubuntu installation? You probably want to update the system packages and pull any security updates. So we're going to do that. We're going to do exactly that in here. In this case, since we're using Ubuntu, we're going to use the apt package manager. If you're using a Red Hat image or a CentOS image, you're going to use yum or DNF. So in this case, we're going to run these commands as we would on a Linux virtual machine. So the first thing I'm going to do is run apt-get update, and that's going to go out and it's going to pull any updates to this base Ubuntu 18.04 distribution. And the second thing I'm going to do is I'm going to run upgrade, which is going to take anything that's new and needs updates. It's going to upgrade them. And if you see, there's not much. There's only two packages that get upgraded, and you see it's stopping and it's prompting me to ask me to continue. So I'm going to say yes. Now we're going to note this for later because when we get to the Docker file section, we can't have pauses like this. But fortunately, apt-get allows you to get around that, and we'll show you that in the next section. Okay, so now I've installed the two packages, and I'm all set. So that kind of takes care of the base OS. So now we've got the base of our container is Ubuntu 18.04. We've now updated it, and we've updated the packages. So what's the kind of the next thing we need to think about is our requirements. So in this case, we've got a simple Python script, and so all we really need in this case is Python. So we're going to install Python 3. And if you look back at the Python script, it's a fairly straightforward one. All we need is a standard Python library. So there's no other Python modules to install. So again, we're just as we would on a virtual machine, we're gonna apt-get install Python 3. In this case, it's installing 18 new packages. And again, as with apt-get upgrade, it's gonna pause and ask if you want to continue. I'm going to say yes, and it's going to install those 18 packages. Now, I believe this is going to install Python 3.6.9, and we're going to test that. And of course, Python 3.6.9. So at this point, if you had your Python script had requirements on a certain version, at this point, you'd want to make sure that you're installing. Say you need Python 3.9 or above, right? You're going to want to make sure you install Python 3.9 there. Now we installed it here with the apt-get, the OS package manager. There are a variety of ways you could do it. You could install at this point. You could install an Anaconda or Miniconda distribution. You could install directly. You could compile it if you wanted to. There's a bunch of ways to do it. Simplest way actually is with the package manager. That's what we did here. But if you had other requirements, you could install a different version of Python that way. So we're okay with, in this case, with Python 3.6.9. So we're going to leave it at that. So the next bit is, so now that we've got our base OS, we've got Python. So we've pretty much got all requirements. This now is to install and kind of test your code inside that container. So in this case, if you remember, when I ran the container, I bind mounted the current directory on the host system, which had my Python file and my Docker file, into the container at /code. So I'm going to cd into /code, and sure enough, you see the Docker file and the Python file. So in order to make this file runnable, we're going to make it executable. So I'm going to chmod plus rx that py.py file. And you can see now that py.py file is executable and runnable by group and other. So now I'm gonna CD back to test that. I'm gonna CD back into home. And another thing I want to do is since I want to be able to make that Python script runnable from anywhere. So I'm gonna modify the path. So in Bash, I'm in typical Bash shell, right? You're gonna export the path. I'm gonna put /code in front of the current path and export that. And if I echo path now, I can see that /code is at the front of the path. So the fact that I'm in home, there's nothing in here. If I do which PyPy, it now shows us that which PyPy is located in /code. So now we've got our code. It's executable. And now the final thing what we want to do is test that the code works inside the container. So I'm going to run py.py, and the py.py script, if you look, we go back up here and look at it. Basically, it takes an argument, which is an integer, which is the number of attempts, which is basically the number of random points to try. So we're going to give it a sufficient amount. So say 1,000. So you can see that with the simulation, 1,000 attempts is obviously not enough. That's a not great estimation of pi, but you can see is if you ran it again with more attempts, it starts to get better. And it's getting better and better. And you can also see as we're running it, as you're adding more points, it's taking longer and longer to run. So right, so this time with 1 million points, it's taking a little under 3 seconds. Okay, so what have we done? What have we kind of showed here? So what we've got now is we've got a functional installation of py.py in our container, and so now it's probably a good time to show, like, well, how did we get there? So if you know Unix and Linux very well, there's a history command. So I'm going to type history, and if you look at that, it will show you a list of all the things we typed. There are some spurious commands in there, like LSs and CDs, but this is basically the recipe for what we did in order to get that installation of Python working inside the container. So I am going to cut and paste that and save that. I'm going to exit out of the container. Now, as John showed, the container is not running, but it is stopped. So it is exited. So you can see with a Docker ps-a will show you all containers, including ones that are running or are finished running. So in this case, I could hop back into that container if I wanted to. I'm not going to in this case, or I could delete it and get rid of it. But while I'm here, I'm going to open my Docker file up with whatever your favorite editor is. I'm gonna paste in that, temporarily paste in that history, so we have an idea of kind of what steps we did, and eventually, and in the next section, we're going to translate that into a Docker file. So at this point, before I move on to the Docker file, do we have any questions? Not seeing the chat. So, John, Joe, any questions in Slack?
I think you're good to go. I clicked away from Slack. Let me just double check. You're good to go.
Okay. So now we've proved that we have a container. We've got our code working in that Ubuntu 18 container. Everything is good. But so that's kind of, I kind of use that kind of what we would call interactive installation to kind of test that. Now you could very well have jumped into that container and saved it, as John mentioned in the first section, and saved it as an image. You can do that. It's not bad for testing. We don't recommend it. We recommend building from a Docker file because you have a recipe, and then in addition to that, that recipe can be stored in source control like GitHub, and so you're making this thing reproducible, and you're showing provenance for everything that you're doing. One of the issues with kind kind of building up a Docker container interactively is you kind of lose, if you want to build from that as a base container, you're kind of losing the base image and you're losing the instructions on how it got there. You don't really know how it got there. So you're much better off and much cleaner building from a Docker file. So that's what we're going to do in this section. We're going to kind of take what we learned in our interactive installation, and we're gonna build it up slowly with a Docker file. So John in the first section showed you a little bit of his Docker file. We're going to kind of go through that in more detail based off of our history, and we're going to kind of build that out. So I'm going to open my Docker file in VI. You can open it in whatever editor you choose. So the first Docker file command. There's not a whole lot. We're gonna cover the basic, the few basic ones I use all the time. The very first basic one you're going to use is the from instruction. So this is basically saying, I'm going to build this container from what base image. So as we determined before, we want to use Ubuntu 18.04, right? So type the from command, Ubuntu. That's the name of the repository on Docker Hub, and the version is 18.04. Okay. So one of the things you'll also see is a tag called latest. And basically that's usually the latest thing that was built. We tend to avoid using that latest tag. That latest tag will travel and change with the version. So if you're trying to build a reproducible image, you really want to pull an exact version so that every time you build it, you're getting the same version, which makes for a much more reproducible container. Okay, so what's the next thing we need to do? Okay, so the next important step, if we look at our history, was apt-get, update, upgrade, and installing that Python version, right? So how do we do that in a Docker file? Well, the important command for running commands is the run instruction. So we are going to prepend apt-get update with the run command. Now we can also do that for apt-get upgrade. And our apt-get install. Now, if you remember, I mentioned in the previous section, and you saw that when you run these commands, they're somewhat interactive. At least upgrade and install are interactive. They're going to ask you, well, we can't really do that with a build file with Docker build, so we need to come up with a way around that. Fortunately, we're lucky in the case of apt. Apt provides a flag for that called -y, which will basically answer yes to all the questions it comes up with in the install process. So we're going to add a -y to that. And a -y to the Python 3 install. Now, the one thing you need to know about these Docker commands is the run commands and copy commands will build each time they're run will create an intermediate layer. So a Docker image is basically the layers upon layers built on top of each other. So in order to make it more performant and more efficient, we want to reduce the number of layers that we build into our Docker file. So while this is a perfectly fine way to build a Docker file with these 3 consecutive run statements, what would be even better, because these are actually all related, is to put them all into one command. So what I'm going to do here is I am going to concatenate these commands together and separated by the double ampersand. And what that's going to do is going to put that all into one layer. So these are all related there, and it's going to build, and it's going to run these 3 commands one after another and put them all into the same layer. Now that's helpful, these layers, especially if you're running, if you're testing out a build and you're building consecutively, is the Docker is really good about caching things. So as it's building the file, the very first time you run it, it's going to run this run command. It's going to pull that Ubuntu 18 image. And the next thing it's going to do is going to do this run command, which is apt-get update and upgrade and install Python 3. So as it's building it, it's going to cache these things. So if I were continually to run Docker build, if I ran it a second time, if nothing in these things have changed, in this case the from and the run, it's going to pull from cache, so it's going to run really fast. So you'll notice, and we'll test this out. If you run a Docker build command, twice in a row, the second time it's going to be super fast because it's going to pull everything out of the cache. So you kind of want to build your Docker file with that in mind, where you the order is kind of important. So you want to put your heaviest and least changed things at the top, and the lighter and more heavily changed things at the bottom. So you kind of keep that cache intact and you're not buffing the cache. So what happens if I have a long Docker file and at step 2 I change something, what's going to happen is immediately Docker is going to detect that the cache is something has changed and it needs to break the cache. So then from that step and every step below it, it will run it out and not use the cache. So if you're kind of running Docker build continuously, you want to try to keep that cache intact to speed things up. Okay. So if we kind of look further down into our history, we've now got Ubuntu, we've got apt-get, we've got our dependencies in Python installed. This Python version, not really important in Dockerfile. We'll test that out when we actually get our container running. So we don't need that. We don't need our code. So what we need now is we need to get our piece of code, py.py, into the container. So there's a couple ways you could do that. In this case, we're just going to use the copy command. What this does is it copies py.py from the build context, which is the current directory, and it's going to we're going to put it in /code py.py, and you'll notice we haven't made that directory. So one nice side effect of the copy command is if there's a directory path, it will make that path. So in this case, it's going to make that code directory. We don't need to actually explicitly make the directory. So there's other ways to do this. You could also wget this py.py file from the web. You could we'll show you eventually how we're gonna put this stuff into a GitHub repo. You could clone and pull your GitHub repo. There's many ways to do this. We're gonna keep it simple in this case, and we're gonna copy our py.py from the current directory. Now there's also another command called add that does a similar thing. It also does some other things like untar things. So, but in general though, if you're choosing between the copy and the add, choose the copy. It's simpler, more explicit, doesn't have any weird side effects. So, okay, now we've got our code copied into /code. What's the next thing of importance from our history is making this executable. And again, we're going to need a run instruction here because we're going to run the chmod command. So now we've got another run command. We're going to change the permissions on this to make it executable. So we don't have very much left. There's a lot of testing left in it. There's a lot of testing in this history. Really the only thing that we have left to specify is that path. So fortunately, Docker make that easy. There is an env instruction. We're going to say path, and then we are going to, again, as we did interactively, we're going to put the /code directory at the front of our path so we can find our py.py file. Okay. So the rest of these are all kind of testing it. None of this needs to be in our Docker file. So that's pretty much it. If we put this all together, we basically got a 5-line Docker file, right? We pulled the Ubuntu 18 base image. We're running the system updates to get Ubuntu upgraded. We've installed Python, copied our code into the container, made it executable, and put it into the path, which is exactly what we did in Interactive. But now we're doing it with a Docker file. So what's the next step? The next step is to actually build that image. So we're satisfied. We feel like we have a pretty good Docker file, so let's build it. So as John showed a little bit in his section, we're going to use the Docker build command. -t is in order to tag that file. So what we're going to do is we're going to give it we're going to give it a name. So the typical way you do this is you give it your Docker Hub username, or or Docker Hub also has the concept of organizations like TACC. So there's a TACC organization. You could give it a TACC prefix. So what we're going to do is I'm going to use my Docker Hub username, and then we're going to name the repo whatever we're going to call it. In this case, we're going to call it PyEstimator : and we're going to give it a version. I'm going to go 0.1. There's a lot of ways you can go. As John showed in the past, our TACC ML images, you can put a lot of things into that version tag. You can do whatever you want. I tend to like semantic versioning. If you don't know what it is, you can look that up. It's basically you have basically a three number with dot version, major, minor, and patch. So we're going to call this 0.1 for our purposes. And the big thing you don't want to forget is that dot. A lot of people, when they run the Docker build, they miss that dot. Now that dot is specifying what the Docker build context is. Now, so the Docker build context is our current directory. So that's where the Docker file is residing. And you'll notice that in this command, you don't see me specifying Docker file anywhere. That's because by default, Docker build will look for a file called Docker file. So if you have a Docker file that's named something different, or you have an extension or something, then you need to actually specify it. You can do that by using the -f command, and you can specify your Docker file. But in this case, we don't. We have a standard Docker file. We're in the current build context, and we're going to say build. Off it goes, and you can see it's exactly replicating the steps that we saw when we ran this interactively. Right now, it's on the second step. It's running apt-get, pulling in the package lists, upgrading the packages. And you can see it's because of that -y option. It's automatically answering yes to those and actually doing all the installs. Now it's installing Python. Copied in the code. Oop. We had an error. Oh, my bad. Got the /code. And here you'll see an example of the fact that I'm running this build again. That you can see the first two steps. The first are cached. So it went through this really quickly, and then it made the permissions change and exported the path, and you've got a fully built image. And you can see if I run it one more time, it just goes right through. So all of the layers are coming right out of the cache. So it takes almost no time at all. Okay. So now we've got our image built. Let's make sure we've got it. Look at Docker images. You can see right here at the very top, PyEstimator 0.1, created 32 seconds ago, 144 megs. So this is a very tiny image, which is good. There's not a whole lot to it. So if you needed to kind of change, if you kind of made a mistake with the tag, you could change that with the Docker tag command. If you wanted to remove it, you can remove it with, as John mentioned, with Docker RMI. At this point, we've got our image. Let's test it out. So the first way we're and this is typically a workflow I use as well. Once I've got my container, my image built, I will run a shell into that container and kind of test it and poke around and make sure that did everything install the way I thought it would. Are things installed in the right places? And does it actually work? So we're going to do that here as well. And we're going to run Docker run again. This time we're going to use the --rm command, which I think John explained in the previous section, will remove the container after we exit. So as you saw in the first case when we ran that first example of Docker run with the Ubuntu container, that the container kind of hung around in the exited container hung around in that PS list. This way, immediately after it exits, it will remove it so it doesn't hang around. So it kind of keeps things clean as you're working around. Again, we're going to use -it again because we're going to get an interactive shell into this container. I'm going to specify my PyEstimator container with the version 0.1. And the command I'm going to run when I get into that container is bin bash. Okay, so good. We're into the container. as root. We're gonna ls the ls-l the slash code container to make sure things are installed. You can see, yes, our pi.py is installed in that slash code directory. It is also executable. Now we're going to test running our pi.py. Yes, it works. So we now know that our newly built image now running as a container is things were properly installed, and our pi.py estimator works fine. So we want to test it one more final time. We're going to test it outside the container. We're going to test running the container without shelling into it, or what I would call non-interactively. So we're going to exit out of the container. That container gets deleted. If I do a Docker PS, oops, I can see that container is not there. That Pi estimator container, so it's not there. It was removed by Docker. So now let's run it non-indirectly. I'm going to use -rm again to remove it when it's done running. I'm going to specify my Pi estimator container. And now I'm going to specify pi.py, the command to run inside the container. A million tries. And bang. So now we know our container works well. We've tested it in both interactively and non-interactively. There's no errors. So now our container is built and we're ready to share that. Let me poke at the container a little bit. So John kind of showed this command a bit before, this Docker inspect command. What this does is it just kind of gives you in detail in this JSON file here what all goes into the container. So you can see a bunch of things. So here's the environment that we specified. You can see the environment with the code in the front of the path. You can see things like the architecture. This is an x86 based image. You can see things about the graphic driver. You can see a little bit about the layers, the 4 different layers that we built. So it kind of gives you a feel of what's inside the image. Okay, so now that we've got our image, we're ready to share it. So this is probably another good time to stop and pause a bit. If there are any lingering questions.
Joe's been answering a lot of the questions in chat.
Is there
Yeah.
anything that we? Okay.
There's nothing right now, but this is a good opportunity to pause. If you have questions, please.
Yeah. Also, take a minute to stretch. And we'll pile into the last section. Okay. Joe seems to have answered all the questions. Okay, so in the final section, we're going to talk about sharing your image. So we've gone to the trouble of building up our code. We've put it into an image, into a container. Now we want to share that with our colleagues, and we want to publish that. So in order to work this section, you're going to need, of course, Docker installed, but you're also going to need a Docker Hub account and a GitHub account. So the first thing we're going to do, and this is probably out of order, I would probably, were I developing this code, I probably would have started my code base with a GitHub repo and been building it and committing to it and keeping it in version control right from the start. But we're going to kind of do this at the end anyway. So again, in the spirit of kind of promoting reproducible science, we're going to put it in the GitHub repo. That way you've got not only your code, but your Docker file in a GitHub repo. So if anyone wants to, you can point, so if anyone wants to use your image, you can point them at your GitHub repo and they can look at your Docker file and see exactly what went into it, what was built, how it was built. I know for me, that's comforting. If I'm going to use someone else's image that I'm not sure about, if I can see their Docker file, I can see how they built it. Makes me feel a little better about using it. Okay. So we're in our Python container directory. We've got our Docker file and our Python file. I'm going to head over to GitHub, and I am going to create a new repository, and I'm going to call this PyEstimator. I'm going to leave it public. I'm going to ignore, right for now, ignore README and a license. Just create the repository. Now GitHub makes this really easy. Right now we've got a kind of a blank repository. We've with a URL to it, and it basically gives you the steps for exactly what to do if you to turn your existing repo, your existing code into a GitHub repo, and then how to share that or how to sync that with your repo on GitHub. Now, for anyone who doesn't already know, Git is a distributed source version control system. So basically, you've got a repo, you've got a local repo on your system. You're going to create here, and you've also got a repo on GitHub, and what you're going to do is keep those in sync. So one of the kind of steps that I kind of walk through is I'm assuming that if you've got a GitHub account, you're using an SSH key to make the authentication easier. So you're either having to use HTTPS and type in a user and a token, or SSH. SSH is much easier. It's not really that hard to set up SSH. Basically, in GitHub, in your settings, you have SSH keys. Basically, you would just kind of create a new SSH key and copy your public key, paste your public key here and save it, and that allows you to deal with run GitHub Git commands against GitHub without a username and password. Makes it really easy to do. So we highly recommend if you're going to use GitHub to set up an SSH key from your laptop, from your Linux VM, wherever you're committing code and working on code from. Okay, so we've got a repo created. We're gonna head back to our directory, and we're gonna create that Git repo. Basically, these steps are exactly what is specified here in on the GitHub example page. Well, the first thing we're going to do is we're going to run git init. That initializes this into an empty Git repository. The next step is we're going to add star. Now, that basically adds all the files in this directory into Git control. If we do a git status, you can see that it's now got two files, a Docker file and the py.py file to put under version control. The next thing we're going to do is we're going to commit. We'll actually call it first commit. And you can see two files were changed. And the next thing we're going to do is since we're working in our local repository, we could continue working here and committing changes and saving changes. But all that would be in your local repo. So what we want to do is synchronize this with GitHub. So if we go back to the instructions, we're going to cut and paste this git remote command and run this back here. So what this does is it adds the PyEstimator Git repo on GitHub as a remote called origin. And if I type git remote -v, you can see I've now got that PyEstimator GitHub repo as the origin for fetching and pushing for GitHub. Okay. The next thing we're going to do is we're going to name our branch. We're going to rename it to main. And then the final thing we're going to do is now we've got our two repositories linked. We're going to push our changes up to origin. We're going to push the main. Oop. You know what? And I don't have my SSH key done here, so I'm gonna have to do it. Oh, you know what? I did. My bad. Okay, that's better. Okay, now I've got what I actually did was pasted in the wrong remote repo. I used the HTTPS instead of the SSH, which I really wanted was the SSH. So hopefully now I've gone back and corrected that. Now with git remote-b, it's showing me that I'm actually using the SSH version. So now let me retry that push. This time I used my key and worked, and you can see it's now pushed it. So now if we refresh this page, we'll see that we've got our actual repo up here. We've got our Docker file and our Python file. And the final thing we want to do is since we're using versions, is we want to tag this release on GitHub as well. So what we want to do is make that version on Docker Hub, which we're going to push to in a little bit. We're going to match that with what we have in GitHub. So what we want to do is run the git tag command. And since our first version is 0.1, we're going to tag it with 0.1 and call it first release. If I run git tag, you can now I have a 0.1 tag, and then finally I want to push that tag up to GitHub, and now we push it up there. So if we go back to here and we refresh, we can see we've got one tag, and if we look under here under tags, we see we've got our 0.1 version. So now we have this locked in. So we have a 0.1 version, and you'll see in the next hands-on exercise, I'll show you, we'll create a version 0.2. You can see you can go back and forth, and so if you have a user who wants to use your old version, you'll have your old version tagged in your GitHub repo, and you'll also have an old version of the image you can pull on GitHub of that first 0.1 version. So users can pull the exact version they want to use. So what's the next step? So the next step is we've now got our code and our Docker file up in GitHub. We feel good about that. The next thing we want to do is we want to push this image up to Docker Hub so we can share it with other people and they can pull it back down. So the first thing you're going to want to do is Docker login. So I've already done this. I've already logged in before, so it's already authenticated with my existing credentials. If not, it's going to ask you for your Docker Hub username and password, which you should type in, and then it will store those credentials. You can log in later. So the next thing we want to do is actually use the Docker push command. This is going to take my Pi estimator, my 0.1 version, and it's going to push it up to Docker Hub. Okay, push. Let me head over to Docker Hub and refresh over here. You can see I've got a Pi estimator. Now I've got other versions here, but you can see the 0.1 tag that I pushed a few seconds ago. So it's now up on Docker Hub, and I or any user or colleague can pull this back down. Let's really test this to make sure this actually worked. So I'm going to make sure. I'm going to try to turn this machine into another user pulling the code in. It has doesn't have the code, doesn't have the GitHub repo, doesn't have the image. So I'm going to remove our created image. So I'm going to try to clean this machine to prove that we're actually pulling the code fresh on a fresh machine, and it's just going to run and work. Okay. I'm even going to remove Python container. So now I'm in my home directory. I've got no code on my machine. I got rid of the GitHub, I removed the GitHub repo, I removed the image. So now I'm going to pull this right back down. So you'll see when it pulled some of the layers already. I didn't totally clean. I didn't get rid of all the Docker cache. So some of the layers already exist. So that's why you see it did download the image, but it uses some of the layers. So that's why it happened quite quickly. So now I've got my image, Docker image. So now I'm actually going to run that. I'm going to use the --rm to delete it when it's over. And there we go. So I've got no code on the machine. I got rid of all the old containers. So this is basically simulating. I'm an end user. I've got nothing. I've got none of the dependencies. This is actually an Ubuntu 20 system. I just pulled the code. It's running in the container, and it works perfectly fine. Any questions so far? So, if there are no questions, I'll continue on. So what I want to do is, I actually like this last exercise. This is basically kind of giving you an example This is our kind of an example workflow. So you've got code. We've got it in a GitHub repo. We're developing it. We're building a container. We're pushing it up. So now we've got our first version of the code working. We've proven that it works in the container. We push it up to Docker Hub. We've synced it to GitHub. Now we're going to continue working on the code to make it better, and we're going to push out a second version. So in my case, since I squashed my repo, I'm going to need to pull it again.
Okay, when you're typing commands, could you seriously slow down? Like you type 3 commands and then reset the terminal, and so we saw none of them.
Sorry about that. So I'll redo that again. Sorry about that.
Yeah, thank you.
So in order to prove that my in the previous step that I was able to pull the container and run it I got rid of the old repo. So I got rid of all the code. So what I did to get back to where I was I went back to GitHub.
Mm-hmm.
I grabbed the URI, and then I used git clone with that remote URL specified, and I cloned that to my hard drive. So now I have a direct a repo called PyEstimator, which is what we committed before, and I'm now in that directory. So now I've gotten back to that first version. So I've now got PyEstimator. I've got it on my system again. You wouldn't typically do this. The only reason I deleted it in the first place was because I wanted to prove that this wasn't running locally off of my Linux VM. It wasn't running off of a previously built container. It was working on a freshly built container. So you wouldn't typically do this. So now I've gotten back to where I was before. So now I'm back at my baseline. I've got my 0.1 version of code in my local GitHub repo. can type git tag. I can see I've got 0.1. Type git log. I can see the only tag we have is that first commit tag. So now we're kind of back to where we were before I deleted the file.
And this is what you just checked out is the code itself, not your container or whatever.
Correct. What I checked out was what we initially checked into GitHub, which was the Docker file and the Python file. So now we've got some ideas on how to improve that Python file. So what we're going to do is we're going to kind of go through this kind of development workflow. We've got our code. Now I want to improve this Python file. If you look at the code on the left, you'll see all we're really going to do here is we've decided that we want to add an argument parser into our Python file. So what we're doing is using the argparse, the Python standard library argparse library to instead of just passing the number of attempts with just a command line argument, we're going to use a proper Python argument. So if you look at the Python code on the left, those 24 lines, the stuff highlighted in yellow is the only things we're actually going to change. So what I'm going to do actually to simplify this is I'm just going to wget this PyUpdated code instead of actually typing it out to speed this up a little bit. I'm going to paste in that PyUpdated code that we have. And now you can see I have this PyUpdated code in Py. So what I'm going to do now is I'm going to move that PyUpdated code to py.py.
Right, in lieu of editing it.
In lieu of editing it, right? So I'm just doing this to speed this up, so you don't have to watch me type. So now we're back to two files, right? We've got our Docker file, we've got our Python file.
Your git status will show that file has been modified. So
and you can kind of see from my prompt too. So now we can see we've modified that py.py file. So if I do a git diff, you can see what's changed as I've added in all these changes that were highlighted in yellow on the left. You've got the argument. I'm adding in the argparse, and I'm adding in a thing called attempts, which is an args number. So those are the only changes in the Python file. So what we're also going to do, and I'll actually type this one out to make it different. We're going to add another Docker file command called command cmd. I think John briefly talked about this in his section, but we'll talk about it a little more. So I want to open up the Docker file in VI, and I'm going to add this. So what this command does is this basically sets a default command. So when we were running our containers, you saw at certain points I was using bin bash to get a shell into the container, and other points I was running the Python script. So this is basically saying if with the Docker run command I don't specify a command to run this instead. So this is basically setting a default command to run if one is not specified. If you do specify one, it overrides what this default is. So what we're going to do is we're going to say, to make this easier on the end user, if they don't know what our container does, is because we just added a help with our argparse, right? So what we get for free with argparse is a -h option, which prints out the help for that command. So what we're going to do is if someone runs our container and without specifying command, it will run the help for the py.py command, which is inside. Okay, so I add that in. I'm going to save that. Okay. So now that so now if I do git status, you can see that I've got two files changed, but both my Docker file and my Python file have changed. And what I want to do now is I want to commit those changes back up to GitHub. So I'm going to run git commit, and I'm going to say my comment is using arg parse to parse args. So now we've now committed to our local repository. We've committed those two changes, and you can see by now typing git status that our branch we're in sync here, but our branch now is ahead of the main branch on GitHub by one commit. So now what we want to do is we want to push those updates back up to GitHub. Okay, we've now pushed the changes up, and if I go over to my GitHub window, you can see now that we've got more commits, and you can see in addition to first commit, the commit I just committed using arg parse to parse args. Now we've gotten more change. We've gotten a second set of changes added to our repo on GitHub. So in keeping with our versioning system, what we want to do now also is we want to tag this. So we want to tag this here in GitHub. We're going to call this 0.2. Now, if I type git tag, you can see now locally in my repo, I've got two tags, 0.1 and 0.2. And finally, I'm going to take that, I'm going to push that up to GitHub. And if we go back over to GitHub, and refresh again, you can see now I've got two tags. And if you look at the versions, you see now I've got a 0.1 and 0.2, and I could toggle back and forth between them, pull those changes out directly, and so to finally top that off, I'm going to build again. Since we made changes to our Docker file and our Python file, we want to rebuild our image. I'm going to call this one 0.2 because it's different, right? And our build context. Now, again, you can see since this Docker file, if you look at the logs, you can see that certain things didn't change, right? So the first step, pulling that didn't change. We have the same Ubuntu 18.04. The apt-get update and upgrade and install Python 3, that didn't change either. That was pulled from the cache. Third step, our py.py file changed. So Docker notices that and says, okay, that's changed. So I need to copy a new file into the container. And again, at that point, the cache broke at that step. So now every step after that is going to be brand new. So then again, it runs change mod on that file, sets the environment and sets that default command, and we have a new version. So if we look at Docker images, we can see we've now got two versions of PyEstimator. We got 0.1 and 0.2. So what we're going to do now, in order to share it, again, go back to that step of sharing it again, we're going to push our PyEstimator, our version 2 up to Docker Hub. Okay. So now if we go back and refresh here to our PyEstimator repo on Docker Hub, you can see I've now got a 0.1 and a 0.2, and I can pull them out. I can pull them out directly. So now at this point, our user of this tool could pull out version 1 or version 2, depending on what they need. And they're all stored nicely at Docker Hub. Also at GitHub, all of our changes there, all fairly transparent. And let's actually run this here to make sure it actually works. I'm going to run this locally. Now, the first thing I'm going to do is I'm not going to specify any arguments. And so what happens is at this point, since I didn't specify a command, it takes that cmd command from the Docker file, right? Our default command is now running the -h, the usage, right? The py-py-h. So it's printing out the help. So now if a user of this tool didn't really know what was inside. Now we have got a nice hint at what's inside the tool. I would probably fluff that help out a little bit to have a little more explanation in there about what it's doing. But at least at this point, the user has somewhat of an idea of what's running inside the container. So again, we can also specify pi.py. And again, this should still be working, and boom, still works after a million attempts, 3.14036. So that's working. So this is kind of a typical kind of development workflow. You kind of work through, kind of build your tool or your tool and kind of build it up in a GitHub repo, storing things in GitHub, pushing it to up to GitHub. When you get to a level you like, save a version, build that Docker container, try to keep the versions between Docker Hub and GitHub in sync. And one thing that we don't quite talk about here, that is really helpful, and I think we will probably add to a further section at some point, is there are kind of automated, GitHub offers automated ways of building a Docker container. So if you're not familiar with this, this is something cool. It's called GitHub Actions. And you can see right off the bat, the first one suggested for this repo is a Docker image. Now, we're not going to do this. I just want to show you what this does. So basically, what this means is that we could fill this out. So basically, what this means is we can have this set so that so by default right now, what this would do is on pushes and pull requests to the main branch, what that would do is it would automatically build our Docker image, and we could have it pushed, and we could also push that further to Docker Hub. So this is just kind of a stub, but you could flesh this out and have it so that your builds are automatically kept in sync by triggering any pushes or pull requests or to specific branches to GitHub. Automatically build out your Docker image and push it to Docker Hub, keep it in sync automatically. This is really useful. We'll probably flesh this out a little bit and put it into the examples at a later date. But I just wanted to make you aware of the fact that this can be done automatically to keep things in sync. So the final thing I wanted to talk about before we break for lunch is a few considerations when building Docker images. So I mentioned the CMD command for Docker files. There's another one called entry point, which is very similar. It basically tells you what to run when there's no command specified. For kind of tool-based images like we did here with our Pi estimator tool, you want to avoid entry point. Entry point is mostly used for services, and the one tricky thing with entry point is it can be overridden, but you have to explicitly do it in the Docker run command. You'd have to explicitly say like Docker run -- entry point like bin bash. So we tend to avoid using entry point and use command instead when you're talking about building kind of simple tool-based containers and images. Again, if you're going to use command, I think we find it really helpful to print help text as the default command. That usually works really well. I did mention this earlier. When you want to copy things into the container, using the copy command instead of add. Add does a few things. I know it does a few things with repos, and I know it does it will untar a tarball. So I tend to like the simplicity of copy over add. Again, another thing we talked about was order of operations. So as you're building out your Docker file and testing things, right, you want to keep the things that change, the heaviest things that change least frequently up at the top of the file, and kind of build and the things that change that are lighter and change more frequently at the bottom of the file. Kind of keep your cache intact. That will keep your builds fast. Another thing to do in relation to that is, if you're familiar with GitHub, there's a .gitignore file. In that file, you can basically specify things that Git when you push things and commit things to Git should ignore. So Docker also has a similar thing called Docker ignore, and that is for specifying things that you want to keep away from the Docker daemon and things getting pushed into the build context. So if you've got, so what people typically do is they'll have a fairly complex code base, and they'll add a Docker file into that builds that. So if you've got like log files, temp files, things like that, these are things you might want to put in your Docker ignore file that will prevent it from. So these are things that aren't needed by the Docker build and aren't needed by the context. So it's not a bad idea to kind of put those things in Docker ignore to prevent them from being sent to the context at all. You'll notice if you do a Docker build in a really big directory, you can actually watch it as it's sending the things to the Docker daemon, sending the things to the build, and it's indexing all the files. So you want to minimize that. As usual, try to keep the images small, keeping unnecessary files out of the image. We didn't really talk about it, but there is, if you really want your images small, there is you can base your images off of Alpine Linux, which is really tight. So instead of using Ubuntu or CentOS or a major main, or Debian, a main Linux distro, you could use Alpine. Things like avoid using the latest tag. Use explicit tag callouts all the time, because what you want to do is kind of lock your Docker file, or you want to lock into versions. Pretty much anything you do, it's usually a good idea to lock into versions. If you're doing lots of builds on your system, there's a Docker system command. Docker system df will show you a list of all the disk space used by containers and images. And there's a command called Docker system prune, which will free up that space. So any kind of unused layers, volumes, I think you can specify volumes, things like that. It'll basically clean it up. The final thing we didn't talk about, we didn't really talk about multi-container pipelines and things like that. So if you've got multiple tools that you want to work together, at that point you're kind of getting into the realm of container orchestration, and you're talking about things like using a tool called Docker Compose, which will run multiple containers at the same time. A typical example of that, it would be if you've got a tool that's running maybe a web tool that's running an API, and there's a backend database to that. So a Docker Compose file would start up both the database and the web front end and let them talk to each other. We don't really talk about that here, but that's something to look out for if you're getting into the area of multi-container pipelines. And the final thing is, a good rule of thumb is, this is kind of the Unix way, is kind of one tool or process per container. And if you've got a multi-step pipeline or workflow that you want, and kind of one runs tools and spits out output, and the next one takes that output and runs analysis on that and puts it to the next tool. You kind of want to have them in separate containers. You kind of you don't want to fill one container with multiple tools if you can avoid it. Sometimes you can't, but in general, a good rule of thumb is one process or tool per container. At this point, that's all I got. It's now 12:02, so it's probably a good time to break for lunch. Are there any remaining questions before we break?
No, I think.
John?
Yeah,
Joe?
I think we're caught up. Yeah, I think we're all caught up in questions. There have been some while you've been going through, which is great.
Okay, great. Well, that's pretty much all I have for containerizing your code. We're gonna break and I guess come back at 1 o'clock for the next section, where Joe will talk about running the containers on our HPC systems here at TACC. So thanks everybody for listening.
Okay. Okay, so yeah, welcome back everybody. We're in the third section now of the containers tutorial here. The first section was really introductory. John did a great job talking about what are containers, what you might use containers for, why containers are important, and a little bit on how to go to Docker Hub and find some containers and download them and use them. And then in the second part of the tutorial today, Eric did a great job with what I think is kind of one of the more interesting parts of this whole thing is it puts you in the role of the developer. You know, you're building your own containers, you have your own tools that you want other people to use. So what sort of skills and commands do you need to know how to do that? And also integrating it with GitHub too, so that you're sharing not just your containers with everybody else, but your Docker files and your code too. Let's see, we have a chat. Are you muted? I don't think I'm muted. Someone can hear me, right?
Yeah, I can hear you, Joe.
Yeah, someone can hear me, so I don't think I'm muted. Okay. I guess, yeah, I said that out loud, but the person who thinks I'm muted probably wouldn't be able to hear that. Anyway, so part 3 of this workshop is, it goes in a little bit of a different direction. What we're actually going to do is we're going to log on to an HPC cluster and see how we run containers over there. Everything we've done to this point has been presumably just on our own laptops. So in order to participate fully in this part of the tutorial, you need a few things. You need an account, a TACC account to log into the cluster. I think everybody's gotten that so far. If you're late coming to this and you're not sure if you can log in yet, just send your username to Lauren Gant in a message on this call, and she can get you access to the cluster. So you need to be able to log in. And it would also be good if you have a Docker Hub account and Docker installed on your local laptop. That way you can build containers locally, push them up to Docker Hub. You can log on over to Frontera and you can download them and run them there. Okay, so while you all catch up, I'm going to go ahead and log into Frontera. So I'm SSHing. This is my username at frontera.tac.utexas.edu. Should ask you for a password. And then you're going to put in your token as well. Okay, so I'm going to have actually 2 terminal tabs open for the duration of this. I'm going to have a terminal in this left tab, which is my local laptop. I'm still going to do some Docker steps like building some stuff over here on my local laptop. And then on the right tab, I'm going to be actually logged into Frontera to run the containers on HPC. And then over here, I have the guide open, and we're now on the 3rd section, the containers on HPC clusters. And if anyone has any questions while we go, Zoom chat is a good place to put it. I have Zoom chat open over here. I do not have Slack chat visible to me currently, but Slack chat is also a good place to ask questions. And I think Eric's in there right now and he can answer questions as well. And also, if you have a question and you just want to unmute and pause me or just tell me to stop and ask your question out loud, I'm totally fine with that too. Please go right ahead and do that. Okay. Let's get started. So HPC systems. So we work at TACC. We have a lot of users who come to use our clusters. They have some software they want to run here. Not all of it is natively installed on our clusters already. A lot of it is like homebrew code that people have written themselves and they want to use on our clusters. Juggling all of these software packages, and it's in the thousands and thousands of different software packages that we need to support. They all have different dependencies. A lot of those dependencies can clash with each other. The module system at TACC is pretty good at resolving some of those dependency clashing disputes. But containers are also another really easy way to solve this problem. And as you know, John and Eric mentioned in the first part of this, containers have a bunch of other advantages, not just making our job easier by managing dependencies. It manages the software for you. You know, you've got now a portable containerized unit of code that you can use not just on our cluster, but anywhere, presumably. So that's that's a really nice value add to your software, is having it containerized for other people to use. The platform that we use on our TACC machines is called Singularity. This is a containerization platform that's designed for HPC clusters, and I'll talk about why in a second here. It's important to know that Singularity, the company, or I guess Scilabs is the company, Singularity is the product, and they've recently changed the name, maybe this was a year or so ago, to Apptainer. It's not called Singularity anymore, it's called Apptainer. It's hard for me to switch what I'm going to say. I'm probably going to say Singularity the whole time, but just know that if we say Singularity or if we say Apptainer, we're essentially referring to the same thing. Some of the clusters at TACC now have Apptainer in the module system, so you can module spider Apptainer to look for it. But I think they all still have Singularity as well, so I'm going to go ahead and just do Singularity for this. But just know in the future, you might have to switch every place where you type Singularity, type Apptainer instead, and it should all work the same. They just changed the name of the tool. So what we're going to do is we're going to get on Frontera. We're going to figure out how to use Singularity to run our containers there. And then actually what we'll also do is we're going to create our own container that actually takes advantage of MPI. So this is going to be a multi-core, multi-node container. And we'll do the same for GPUs. You know, our little toy example that we did on our laptops, it just ran a Python script on one core. But what if you have a tool that you've containerized that uses CUDA and you want to run it on a GPU? You know, this is really big in machine learning, of course. So we'll show an example of that as well. Okay, and let's get started. So if you haven't already, please do log on to Frontera. I mentioned that we don't have Docker installed on any of our clusters. We have something called Singularity. It's follows the OCI standard, which is the Open Container Initiative standard. And that essentially means that if you build a Docker image with the Docker platform, which also follows the OCI standard, then other platforms which follow that same standard should be interoperable on that container. So you should be able to use it with any of these platforms. And that's how we've ourselves have really defined sort of our internal process for containerizing code and running it on the clusters. I really like working in the Docker ecosystem. It's been around a long time. The documentation is really good. The user community is huge. I find it really easy to build Docker images on my laptop using the Docker platform. And then what I'll do is I'll generally push those to Docker Hub. And then when I'm ready to run that container image on a cluster, I'll log on to my cluster and I'll pull it down and I'll do Singularity from there. I'll let Singularity take over, pull it, run it. What I don't do with Singularity is I don't build images. Singularity is you don't have escalated privileges within Singularity on our clusters. You can't become the root user. And that's by design. We don't want people usurping the root user account on our clusters and doing nefarious things. So the way Singularity works is you run as your own username. So my username is W.Allen. So anything I run in the Singularity platform on Frontera, I'm going to run as W.Allen. Whereas on my laptop over here, if I ran something in a container image, by default, I'd be running as the root user. All right, yep. We mentioned this, Singularity is now Apptainer. And so step one, we need everyone to go ahead and log into Frontera. I've already done so in one of my tabs up here. And then what we want you to do next is start an interactive session. And so go ahead and just type this command and we'll see if it works. This by default alone might not work. What I think I want you to do, so while you try typing IDEV to start a interactive job, what I want to show you is what we've done with Singularity on our cluster is we've disabled it from working on the login nodes. Singularity can use a lot of resources, cores and RAM. and it can really overwhelm the processes and power available on the login nodes. It shouldn't be run on the login nodes. We have to run it only on the compute nodes. And so if you try to load the Singularity module, which on our clusters is called TACC Singularity, what will happen is you can load it, module load, TACC Singularity. And now if I try to run a Singularity command, it's going to give me a little warning that says, hey, don't run Singularity on the login nodes. Make sure you get an IDEV session on a compute node and run it there instead. So this is by design. All right, I'm going to see what happens if I just do an IDEV M40. We should all be on a reservation, so this might just suck us into the correct queue by default. Found an active reservation request. You're going to have to say Y for yes. And it should put you on a RTX node. So these nodes on Frontera are, I think there are 16 Intel CPU cores, and they have 4 NVIDIA RTX GPUs, pretty powerful GPUs. Okay, so after just a few seconds, everyone should be on a node. And the way you know that you're on a compute node is your command prompt has probably changed a little bit. If you type host name, you won't see a login node anymore. You'll see one of these C197082 or similar. This indicates that you're on a compute node. And so when you're on this compute node, you're on it all by yourself. You have access to all of the cores, all of the RAM, all of the GPUs available on this node for the duration of this interactive session, which we set to be 40 minutes. So once on the node, the next thing to do is to load Singularity into your environment. Singularity right now is in the module system on Frontera, meaning by default, it's not in your path, but it's extremely easy to add it to your path. Without going into too much detail on how the module system works, you can list modules that are currently in your path. For example, I've got Python 3, CMake, Xalt, a few other tools in my path by default. I've already loaded the Singularity module, so I can see it here. This command here, module spider Singularity, will show some help text and some information about Singularity, and give you some links on where to get more information, some tips on how to use it. I'm just going to hit Q to get out of this interface. And then module load TACC Singularity will load the actual module that's called TACC Singularity and put it in your path. Singularity is an executable located here. And just to prove to yourself that it's in your path, you can display the Singularity help text by doing something like this. Singularity -- help, for example.
Joe?
Yes.
There's also a TACC Apptainer module. Why are we not using that one?
I'm not using it simply because the guide says TACC Singularity, and I don't want to cause confusion, but you are more than welcome to use Apptainer and follow along with this exact same thing. In the future, Singularity, the module, is going to go away, and it'll only be Apptainer. Okay, thank you for the question. So I'm on Frontera, I'm on a compute node. I've loaded Singularity into my path. And now there's a lot of parallels here between Singularity and Docker. And if you are on your laptop and you display the Docker help text, you'll see there's a lot of these subcommands. And I think, oops, my window, there it goes. There's a lot of these Docker subcommands. I think we probably used like 6 or 7 or 8 of them, maybe. We did a Docker build, a Docker run, a Docker push. We did a Docker pull to pull down containers. We did Docker login to log into Docker. You'll see a lot of parallels with the available Singularity commands. instead of doing a Docker pull to pull down an existing image, what we're going to do is a Singularity pull to pull down, an image to the cluster. When we're ready to run that image, we're going to do either Singularity run or Singularity exec, and I'll show both. And let's see, what else do we have? We have Singularity. Honestly, I think shell. So we'll probably also do a Singularity shell today, but that's probably like 98% of my interaction with Singularity is those 4 commands. I'm pulling from Docker Hub. I'm running what's in the container with Singularity run or Singularity exec. And I'm also starting interactive shells inside a container with Singularity shell. And seriously, that's probably 98%. What I didn't mention is I don't do Singularity builds. I don't do Singularity pushes because I prefer to work in the Docker ecosystem. I'm on my laptop. I'm the Docker building there, Docker pushing from my laptop, and then I'll jump onto the cluster. And I don't build with Singularity there. In fact, Singularity build is disabled on our clusters because this does require root privileges to do. So normal users won't be able to do this on our clusters. If you want to download Singularity to your laptop and build there, you'd be able to. And I think, I might be wrong on this, but I believe future versions of Apptainer are heading in the direction of doing rootless builds where you would be able to then build on our cluster safely. And that's definitely something we're going to support and look into if I'm not completely making that up. I don't think I am. I think that's coming. Okay, so yeah, we're going to first look at Singularity pull. So this is how we're going to pull an existing image from some sort of container repository on the web. And in the example here, what we're going to pull is this container right here. It's called GodLoveDC LOL cow. And this is actually hosted on Docker Hub. So if I go to Docker Hub and I search for this container name, pulls up this existing repository, and I can click on it and click the tags tab here. And I see that there's only one tag. It's called latest. So by default, it's going to just pull latest. But if I was on my laptop, I would be doing Docker pull, just this right here. And now since I'm on Frontera, I'm going to do Singularity pull. And I do need to specify that I'm pulling from Docker Hub by adding this Docker URI looking thing at the beginning. So I'm going to go ahead and I'll just type it in. So I'm on Frontera. Let's try Singularity pull. And also I should mention while we're here, if you ever kind of forget how to use a command, you can always do Singularity subcommand and then help again like this, and it should give you some hints on how to use that specific command. In fact, it's showing that I can pull things from Singularity Hub like this, from whatever this is in this format, and there's an example of how to pull from Docker as well. So this is helpful. So I want to Singularity pull from Docker Hub. Let's just pull this one, GodLoveDC/LOL cow. Now, when we, okay. So I kind of gave away the outcome here, but what I'm going to do is I'm going to go ahead and remove what I already pulled so that I can pull it again. And I think it's cached, so it's just going to generate it really quickly.
You got a typo there.
Thank you. Now I just have to see where is the typo. I see it. Thank you. So when I was on my laptop and I did a Docker pull, what it does is it goes up to the web and it pulls these sort of ephemeral layers down into a database that sort of lives behind the scenes on your laptop. You don't actually see a physical file called like my Docker image.doc or something like that. It lives sort of in a database And you can see it by doing Docker images, and that'll list all your images, and you can see it there. But it's not really associated with a physical file that you can move around and play with. Not by default anyway. You can create that file, but by default, we don't really do that. Singularity works a little differently, where when I pull a Singularity image, it actually just writes a flat file onto my file system here with the extension .sif. So this is a Singularity image file. And the one that I pulled, it by default gives it the name. For some reason, it omits the name of the owner. It gives it the name of the container underscore the tag, in which case we pulled the latest tag. And so when I did that Singularity pull command, it generates this file right here. And now this is, you can consider this to be a container image that we can interact with. Just like I interact with Docker images on my laptop, I can interact with this in different ways. I can start an interactive shell inside it. I can just run it to see what it does. I can run it and provide a command at the end, probably to do a different thing. And so let's go over some of those examples of how I would interact with a container that I've pulled with Singularity. So the first example here is with an interactive shell. And in Singularity, they have this nice command shell that basically sets up the interactive shell for you. When we did this with Docker, we had to do a bunch of flags. It was like Docker run --mr --rm -it for like an interactive session. But here we're just going to do Singularity shell and the name of the CIF file. And pay close attention to your command prompt, because it'll change. The verbiage we use is that I'm going to shell inside this container, whereas right now I'm on Frontera. Now I'm on Frontera, but inside this container. So I have access to the contents of the container, and my environment has changed. Let's see. Who am I? We talked about this. On your laptop, if you did this, the answer to who am I, you'd probably be root. When you shell inside a container on your laptop, you become the root user typically. Singularity is different. I'm still myself. I'm still W. Allen. This is nice because when I'm running jobs with Singularity containers that generate output files, for example, if I were root, those output files would be owned by root:root. Like the privileges can get all goofed up. It's kind of messy, actually. So it's nice to be able to run in user space on a cluster with Singularity, because as I am running a job as W. Allen, the files that I have on the cluster, the executables that I have, the output that it generates, it's all associated with my ownership and group ID. ID, this is going to be the same as I am myself. All my groups are here. I probably have more groups than a lot of the people on here because I'm in way too many projects. One thing that's nice is that on our clusters, what we've done is we've configured Singularity to automatically mount a few file systems for you. This looks a little bit messy, but all of the Scratch file systems, home, are by default automatically mounted inside the containers. So if you want to run a job where the executable is inside a container, but your data is just somewhere on the Scratch file system, you don't have to move anything around. You can just run your Singularity executable and point it straight to your files that are already on Scratch and give it a different output directory that's already on Scratch. You don't have to do any additional mounting or moving anything around. It just is able to see it by default. On Lone Star 6, if you're using that cluster, I believe Corral is also mounted inside the container. And if you need some other file system to be mounted, it's pretty easy with Singularity. there's a flag like Singularity dash bind, I think, or dash bind mount, and then you can mount another file system inside the container. I think there's an example of it below too. But it's extremely flexible with and user friendly with not making it hard to access your data from inside the container. So I will exit this container. It'll put me back out on the command line. And let's just run the default command. So there's basically two ways to run the meat that's inside of a container. You can do a Singularity run or a Singularity exec. So run will run the default command. If you remember from Eric's part of the workshop, you had those pie containers that you created, and we set the default command to be like to show the py.py help text. And so that's what's happening here. If I Singularity run the name of that container with giving it no other options, all it's going to do is show me that py.py help text. If I want to run my own command in the container, I use Singularity exec. So I'm executing exec, I'm executing a specific command that I want to run using the assets stored inside that container. And the example here is like when in Eric's section, he would do a singular Docker run name of the Docker image, and he did py.py 1 million, and that would run that command inside the container. So if we want to run py.py, we're going to need to do Singularity exec and then give the command that we want to run. So that's run, that's exec. Let's look at LOL cow. So this is the image that we downloaded from Docker Hub, and it has a default command. So if we just go ahead and do Singularity run, then the name of that image file like this, that's going to run it, run the default command and return the output here. So it's a nice little example. Basically, it uses a short pipeline of a couple different commands. It generates some random text, and then it feeds that text to the executable called cowsay. So it'll show you some, and somehow I think they use curses or something, and they generate some nice colors too on the command line here. Don't you feel more like you do now than you did when you came in? I don't really know what that means, but suffice to say, this is working. Occasionally, yeah, this is a good thing to mention. Occasionally, Singularity, it will grab a bunch of stuff from your environment. And occasionally, without like going into the weeds, what's set in your local environment can occasionally mess with what Singularity is trying to do. And so there's this flag -- clean env that you can add that will help quiet some of the errors that it will throw at you sometimes. So if you ever have a really messy environment and you want to just use a clean environment when you run what's inside the container, just know that there is a way to do that. There's flags to do that. Okay, so we looked at run. And now what if we want to sort of customize the command? That's where Singularity exec comes in. So if you do a Singularity exec, this is going to expect that you're providing your own command to run inside the container. It looks mostly the same here. I'm still need to specify the name of the container image. But the command I want to run is everything that goes after the image here. So I want to feed it the command cowsay and then some text. Containers are great. And so now what this should do is it should run my customized command here using the assets inside the container. So here's my custom command. I guess it did not like my exclamation point. Let's try that again. Let's try to solve this. My guess is I need to escape it like this. Okay. Close enough. So containers are great. And you know why this is cool is because we actually, I'm going to eat my words if we do have this installed, but I am guessing that we don't have CalSay installed on these Frontera RTX nodes, which CalSay, yeah, there's no CalSay here. So if I try to just run the CalSay command by itself, I wouldn't be able to do that. It's going to just say command not found. But with containers, we don't need to worry about command not found ever again. We'll just find the container that contains the executable we want to run, download it, and run it like this. All right, so that's really like the sort of lightest intro to pulling a container onto Frontera and running it. We didn't really do much impressive stuff yet, or much super difficult stuff. Do we have any questions so far about what we've covered? Okay,
No questions, Joe.
great. So clear so far. Oh, I lost my chat. There it is. Okay. Great. So that's good for this interactive session. You can go ahead and hit exit. And what you'll see is that you go from the RTX node back out to the login node, which is what we want to do for the next part. We're going to do something a little bit more complicated than what we've done at first here. So let's see. Yeah. Now we hopped in an interactive session onto a compute node and ran an executable. I'll remind that Singularity only works on those compute nodes, so we can only do that on the compute nodes. That's not going to work on a login node on Frontera. And this is by design because these applications that we're packaging in containers and running typically are high throughput, high performance applications that require lots of cores. They require maybe lots of time, longer than you want to sit around in an iDev session to let them run. So being able to encapsulate your whole job into a batch script and send it to a compute node non-interactively and run it behind the scenes is the important next step. Because we're all going to have applications that we want to run on Frontera that are containerized that might take days or hours to run and might require several nodes or hundreds of cores. And so that's sort of the next progression here. What does that look like? Let's first just grab an example command. I think I need a refresh. I just updated these docs today. So if you're looking at the documents and they don't look exactly like what I'm seeing on my screen, just go ahead and refresh the page. But now keeping in mind that we want to run a bigger job with maybe more resources than one node, let's just start to look at how that looks. Step one is we have to define what our job is, like what command do we want to run? Well, here's an easy example. Let's just run the Python -- version command and pretend that this is our big, fantastic job that we're trying to run. It's a toy example, but this is the command we want to run. Python -- version. And so I don't want to just run this on Frontera either. I want to run the containerized version of Python -- version. And so what I'm going to do is I'm going to go to Docker Hub. I'm going to find whatever Python container I want. And then I'm going to Singularity exec like this. So what you'll see, there's a slight difference here from what we did the first time around. The first example with CalSay, we took 2 steps where we did a Singularity pull my container and then a Singularity run the container. So I first pulled it, generated that zip file, then I ran it, and I ran the contents of the zip file. We're sort of combining those 2 steps into one here. If you do a Singularity run or a Singularity exec and provide it the container URI like this, rather than the name of the CIF file, it'll basically combine those steps for you. It'll first pull it, then it'll run it. And this is a fine way to do it. It's actually not my preferred way to do it. I do prefer to pull as a separate step and then run. I just try to be extremely deliberate about, the steps and what I'm doing, but this is completely fine as well. So let's say this is what we want to do. What we want to do on Frontera is assemble this command into a batch script like this. And so if you're using Frontera, you likely have seen batch scripts before. There's in the Frontera user guide, which is linked right here. It goes into a lot of detail about these batch scripts. So we're not going to belabor it here. But essentially, the stuff we're interested in is it has my command at the bottom, the Python -- version. And I do need to make sure I'm loading that Singularity module as well. So I'll put that in here. And then as far as the SBatch directives, these are instructions to the scheduler about how many resources I want to use. For example, I want 1 node, 1 core. Let's just say, for example, this job is going to take 2 hours. I give it a name. I give it a name for the output file. This part's important. We want to specify the RTX queue. This is where our reservation is. And we also have a reservation for this called containers_training. And so you can specify this with the -- reservation directive inside the batch script. But basically, I'm gonna select this whole thing, and I'm going to copy it into a file. I think I might have already done that. Okay, I did. So I'm going to copy it again into a file. So I just open a file with my favorite editor, maybe Nano or Vim, and I paste it in. And I'm going to make it a little bit bigger so my text doesn't wrap around. Okay, so once I pasted it in, I'm pretty happy with just how this is. I don't need a blank line here. So I'm calling it my job. This is my output file. I want it to go to the RTX queue. I'm requesting 1 node, 1 task on that node. 2 hours is way too long. I'm going to change this to 2 minutes. I'm going to change it to 5 minutes. And -- this is the name of our reservation for today. This is only active until I think 4 p.m. So after this, you'll just have to wait in the queue. I load Singularity, and then I'm going to do this. Now, if I just ran Python -- version on Frontera, it would find whatever version of Python's in my path, and it would produce the output. It would take less than a second. It would be instantaneous almost. When I do this command on a cluster, and this is why I said, oh, I'll just do 2 minutes, and then I changed my mind. I said, well, maybe I better do 5 minutes. Because when I do this command, what's it actually going to do? Is it just going to do Python -- version? Well, not exactly. First, it needs to go up to Docker Hub and pull this image down, put it into my cache, and it's going to generate that .cif file. And I happen to know that this container isn't huge. It's probably going to take 30 seconds to do that. It'll be pretty quick. But I have to account for this in my total job time. But once I've done this once, and then that thing is cached, it's much quicker after that. But like I'll sometimes build some pretty crazy large containers, like 20 gigabytes or so, which is just huge, and they're kind of annoying to work with when they get that big. But sometimes you do have to account for the amount of time it takes to pull down that image. In a 20 gigabyte container, it might take 20 minutes to pull the whole thing and build it into that CIF file. So just kind of keep that in mind. This I'm pretty sure is small. We can go to Docker Hub and look like, well, let's try it like this. Python tags latest. So this is probably only going to be 300 megabytes, not huge. It'll be pretty quick. Okay, so once that is all written to my satisfaction, I will save it. I'm going to remove the output from when I did this morning. And I'm going to go ahead and submit this job, or submit this with the SBatch command. So SBatch is the utility we use to take your Slurm script, send it to our queuing system, and then it's going to go find a compute node for you and run your commands in the background non-interactively. All right, and if you have a bunch of allocations on Frontera, you might just be on the training allocation, in which case it might have just worked. But if you have multiple allocations, you also need to specify the name of which allocation you want to use. I'll just pick one. So this is specific to me. Or if you have your own allocations, you might have to choose one of the ones that you see in your screen. Okay. So it's submitting, and I'm going to do like a show queue-u to see if it'll tell me like where my job is in the queue. And if you do it quickly enough, you'll probably see that it's running. It's been running for 5 seconds so far. And like I mentioned, I think this will probably take about 30 seconds to run because it's got to pull that container image, assemble it into a CIF file. And so if I do show queue-u again, I see it's been running for 24 seconds now, so it's still going. This obviously is much longer than the time required to just do Python -- version. So this, all of this is not really container specific stuff. This is just how we run jobs on Frontera. And it happens to be the job that we're running in this workshop is a containerized command. So I'm going to let that finish. It's probably done by now, but while I let it finish, I'm going to mention a couple quick things. This thing I already mentioned, I think Eric mentioned it as well, but it really can't be stressed enough. Sort of the highest level of the container development workflow that we go through it this way because users, including us, we generally aren't using sudo to do commands on HPC systems. I don't feel comfortable using my root privileges to install Docker and build Docker images on Frontera. That's not what Frontera is designed for. Frontera is designed to run these big production jobs. And so what I'm going to be doing is building my Docker images using Docker on my laptop. Or Podman. I think several people ask questions about Podman. Just any containerization platform that follows the OCI standard. I'm going to use that to build on my laptop. And then I'm going to push those up to a public container repository like Docker Hub. I choose Docker because I've been using it the longest, and it's really great documented. It's very user friendly. I'm just familiar with it. I get how to use it. I don't super want to invest the time to learn a new container building tool. So I really like Docker for this, and I'm happy to push my Docker images up to Docker Hub. And then when we hop onto the cluster, we use Singularity to pull those images down and actually run the contents. So that's how we do it. That's how basically everyone in my group does it. What does this say? If you need to edit text files, yeah, this is just a general note. Yeah. Okay, so a couple differences that I want to mention, differences between Docker and Singularity. And I mentioned a few of these already, but thinking about directories that are mounted, if you're running Docker on your laptop, and you want to mount something inside the container, like your desktop or a folder that you've got all your code in, you actually have to explicitly use this -v flag to mount your local directory inside the container in order to have access to that code or those files inside the container. You have to explicitly do that. On the cluster, Singularity does that for you by default. We've configured Singularity to automatically mount your home, your work, and your Scratch directories, and in some cases, Corral even. So if you have data on any one of those places, you don't need to move it. It's already there and ready for you to be used using code that's inside a container. So ID, remember, if I'm on my laptop running Docker, if I do a who am I, I'm most likely going to be root. You can change that. You can run as another user inside a container, but you have to use some flags to specify what group ID and user ID you want to run as. It's a little bit clunky and it's extra steps. So just like by default, you're root. Singularity is different. Everything I run as myself. So everything I run with Singularity on the cluster is run as me. And it maintains my ownership and group permissions and all that. And then the images themselves, if you remember on your laptop when you're using Docker, the images are stored as separate layers that are all stacked on top of each other, sort of behind the scenes in this Docker database. You don't really interact with the, those images as a file. You can assemble that into a file, and there's really rare occasions where we do that for specific purposes, but I very rarely will do that. Generally, everything is just stored in the Docker daemon or in the Docker database behind the scenes. And I only interact with that stuff using Docker commands, like I'll list it by saying Docker images. Singularity is a little different in that when I go ahead and pull, there still is a cache that it uses. And I think on Frontera, I'm guessing the cache is probably located at scratch/singularity cache. Yeah. So there is a cache. However, it also assembles these .sif files for you that you can move around. You can put them on a different machine. You can run them anywhere. It's pretty nice. Anywhere Singularity is installed anyway.
Hey, Joe.
Yes.
Yeah, but we have a question in chat.
Oh, can you say something about differences in port mapping? Assume I have a Docker container which wants to run a service on a privileged port that won't work. No sudo. So how would I map that port to a non-privileged one with Singularity? So Docker, that's really easy to map ports. There's a flag. I've never had to do it with Singularity, but so I'm going to try this live. I'm assuming it's just as easy. So if I do a Singularity run -jet, well, I have to be on a compute node to do Singularity run. But I'm guessing there's gonna be a flag, like a port mapping flag like this, -p, and then the name of my container, where you can map an inside the container port to an outside the container port. So if I'm on Frontera and I want to interact with port 5000 inside the container and map it to 5001 outside, so now I'm on Frontera, I would ping port 5001 and that would automatically send inside to port 5000. It'd be something like this. I don't know what this flag is. Let me get on an IDEV session and see if we can see that in the Singularity help text real quick. That's how you do it in Docker anyway. I think the developers know that a lot of people are coming from Docker, so they try to make them sort of one-to-one as much as possible. Well, it's not P. Yeah, I don't really want to read all this. I'd probably just Google it real quick and it would just tell me the answers, unless you know it, Eric, and you want to shout it out. Yeah, so what I'll do is let's put a pin in this one. I will figure it out. I don't want to read all this right now in the middle. So let's figure it out like at the next break. and we'll post it in the chat. But I'm pretty sure it's going to be something like that. Yeah. Okay. Let me get out of that job I was just in. Let's see. Let me check. I did show Q-U, and I checked that my job from before is finished now. And this was my job from before, test.slurm. And it should have created this output file, output dot, and then it's going to be the job ID. And it is here, and it should just have Python-version at the end. So now at the very end of it, it's saying Python version 3.11.0. So what else is it showing in here? All of this stuff here is the first part of what I said. It's actually Singularity going up to Docker Hub, identifying the image, pulling it down, and assembling that CIF file. So this is that part that probably took about 30 seconds at the beginning of my job. And if I run this job again, it's going to probably use all the cached stuff, and it's not going to do this again. It'll be much faster the next time. And this is something I want to call out as well. You'll see this if you're running Singularity jobs on TACC resources. You'll see this error in a lot of your outputs. It's a very specific error. Error ld.so. This is a shared object. It's pointing to a specific shared object from the Exalt library. And it's saying from ld preload cannot preload, ignored. This error, it looks scary, but you can completely ignore it. There's a tool we have at TACC called Exalt, which is in your module system by default. And this is basically tracking what executables the users of the cluster run just for reporting and statistics and stuff. And I don't know what the reason is, but for whatever reason, there's some library in Exalt that does not play nicely with Singularity containers, and you get that error every time. It might be the LD preload environment variable, something to do with that. But I always just ignore that error, and you can completely silence that error by just module unloading Exalt like this. That'll remove Exalt from your module system. But we get tickets. It's got to be several tickets a week where people are asking, what does this error mean? And I just want to reassure you that it doesn't affect your job. It's just one of these scary errors that looks more scary than it is, and it just has to do with this Exalt module. You can ignore it.
Hey, Joe.
All right. Yes.
Yeah, I just want to pipe in that someone answer that port mapping question. I think there is a -- network args option that you can use to port map to set a port map between inside and outside ports. But I still believe that if you want to use privileged ports outside the container, you need to use the fake root feature of Singularity, which we don't have enabled.
Okay.
So essentially using ports below 1024 on the outside on the host. Right. You still need to be root. So
right. But you would map, non-privileged port from the outside, something in a like 5,000 range.
You could go the other way, like port 80 inside the container to port 8080 on the outside, which is a non-privileged port. That would work without fake root.
Got it. Okay. Okay. So now we ran that sort of toy test job, which was just Python-H version. Let's do another job that's a little bit more of a realistic thing. And why don't we do py.slurm? So this is going to be a job to run that py.py command that you developed, on your local laptop. You containerized it, you pushed it up to Docker Hub. Let's take that product and run it on Frontera now. This is the really neat thing about this is, my laptop environment is completely different from the Frontera environment. I'm talking, operating system, versions of Python that are installed. They're very different, but it doesn't matter because the tool I'm running, pi.pi, is containerized with all of its dependencies. And so I know that whether I run it on my laptop or run it on Frontera or anywhere else, it's going to run exactly the same way. And that goes not just for me running it, for anybody running it. So this is really, you know, a phenomenal way when you're developing a package for use in multiple environments or for multiple different people to use. It's really probably the best way to do it. I don't usually like speaking in hyperbole, but the containers are amazing and magical. I love them. They're perfect. They're no complaints. They're perfect. All right. I'm sure we could come up with some complaints if we wanted to, but let's see. So what do we want to do? Okay, so actually this part, I'm going to go on to, what am I going to do? Is this on the work file system? Yeah. So I'm going to go to Frontera. I'm going to create a new directory somewhere. In this case, let's just do it on work. You can do it on Scratch. You can do it on home. It doesn't really matter at this point. CD to that new location and open up a new file called pi.slurm where we'll start to work on some of this stuff. So right now I'm in my home directory. I'm going to CD to my work directory. I'll just follow the instructions over here. I'll make a new folder called containers at TACC. And I'll navigate into that folder. And I'm going to open up pi.slurm. I'm going to use Vim because I'm afraid if I use nano, I won't know how to get out. Let's see. So I'm going to use Vim pi.slurm. And I'm just going to cut and paste the whole contents of this slurm script into here. So while you guys catch up, I'll sort of talk about what's happening. You know, the first 8 or so lines here are the same as what we did on our Python -- version job. That first job we submitted. This is pretty much all the same stuff. We're still doing one node, one core, 10 minutes. This is the name of our reservation. We want the RTX queue. And we'll just give it a different name, calculate pi. It's a little bit more of a descriptive job name. So what do we want to do in the actual job itself? So as normal, we need to make sure we load the Singularity module. And I'm actually going to run 2 different containers. So you can see sort of a progression here. And, you know, the real life analogy might be that you have 2 tools you want to run. The output of the first tool is the input for the next tool. So you're forming sort of a pipeline, and that's kind of what's happening here. First, we'll just run that LOL cow container, and this time you see that we are calling out the Docker URI rather than the name of the CIF file. So we'll see what happens when we do it like this. And then let's estimate the value of pi. So Singularity exec. Here I'm doing exec, not run, because with exec, I have to actually, I'm providing the command that I want to run using the assets inside the container. Remember, Singularity run just runs the default command. Here at Singularity exec, I'm providing my own command. And I need to give it an existing pi estimator. I actually didn't do this part this morning, so I'm going to, I believe, Eric, is this your username, Eric SF on Docker Hub? Pi estimator.
Yes, that's correct. Yep.
Okay, so I'm going to borrow Eric's container that he built and pushed up to Docker Hub this morning. And I want a Singularity exec, Eric's pi estimator container, pi.pi is the name of the executable. And then let's give it 1, 2, 3, 1, 2, 3. This is 10 million. Okay, so I think 10 million takes around 20-ish seconds to run. But I have to factor in that it's going to pull this container and it's going to pull this container. The default command in this one is instantaneous, essentially. But, you know, this might take 20 seconds to pull, 30 seconds to pull, 30 seconds to run. This is, you know, this is a 1 to 2 minute job. Let's just say 10 minutes is fine. Okay. So I'm going to go ahead and save this. And I only have py.slurm here in my folder. I'm going to go ahead and submit it. Let's see if I had any typos. Oh, before I do that, I'm going to specify the allocation I need to use because I have multiple allocations. If you don't have multiple allocations, you don't need to specify this. See if that works. Okay. Submitted batch job. I'm going to do a show q-u. Let's see where it is. And it's running. Okay, so I'll give that a minute to run while you all run yours as well. Let's look ahead. Yeah, it says, don't forget to replace username right here with your version or Eric SF if you want to do that. Oh, I guess you could use my Docker Hub username too. Maybe I do have it up there. Let's find out. WJ Allen, Pi estimate. Oh, I think I do. Okay, so yeah, I guess I could have used mine. This was pushed 7 months ago. I guess the last time we did this this tutorial. Yeah, so if you have more than one allocation, you have to specify the allocation name. Go ahead and submit. And then let's look at the output to see what it looks like. I'm going to show Q again. It looks like my job just completed. I see it down here in the completing list. So if I list my files again, I do have an output.slurm. And if we look at the contents of that, what do we expect to see? So I got to scroll up a little bit. I'm scrolling up. Here's the beginning. Okay, this is good. This is informative. So info using cached CIF image. So I know that it didn't pull a fresh container for this. It used what was already in the cache. This is a really long calce. I don't think I've ever seen one this long before. What is a compact city? It's a city that can be guarded by finitely many nearsighted policemen. I don't get it. Maybe I'm missing. I don't know. Seems like there's a joke in there. And then, okay, so calce ran. Now, estimating the value of pi. This was actually, I think I echoed this text. So this echo estimating the value of pi is what's right here. And then what happens next? Well, I hadn't pulled this pi estimator container on Frontera yet. So what it's doing is now it's pulling that container, assembling the CIF file, and then it runs that asset inside. So from 10 million attempts, that was 3.1410. That's pretty good. That's a pretty good estimate of pi. All right, we can do better though. 10 million is a paltry, small, tiny, feeble number. You know, we're on Frontera. We should be doing not 10 million. We should be doing 10 trillion digits, you know, 10 trillion estimates. And so we'll do that next. All right, what else? So let's imagine too, like what happens if I run this same job again, this exact same job? Well, it's probably going to use this same cached image. And down here, instead of pulling it from scratch, it's just going to use the cached version of that image. Singularity run has a flag like -- ignore cache, I think. If you want to force it to pull the latest from Docker Hub each time, you can make it do that. You know, we don't need to get into the details of that flag, but just know that it's possible. You know, Singularity has a lot of these flags that customize the behavior, which is nice. So this was I think this was a successful example. We didn't really show off the power of Frontera yet or the use of GPUs, but that's going to be next. But yeah, we've basically gone through really the essentials of so far. We've gone through really the essential stuff of what we're working here and what we're trying to show you how to do. Is that, you know, you are the developer. In some cases, you are the developer. You have created tools that you want to containerize. Now you want others to use it. You know, how does Eric use your tool on Frontera? Well, all you need to do is you build the container, you push it to Docker Hub, and then you say, hey, Eric, do a Singularity pull. Here's my container. and here's the command I want you to run. And he can, he can do that, and it'll run in the exact same way as it ran on your development environment. But also, you might not be very interested in building your own containers. You might just be interested in using existing containers. If you go to the web, if you're a life sciences researcher, there's a whole repository of biocontainers. You'll find tens of thousands of containers and different versions that contain tools for genome analysis or protein structure function analysis. All these tools that life science researchers use that have been installed and containerized already, and you can just use them without having to try to install them yourself on the cluster. It's extremely nice. Either way, if you're the developer or just the user, this sort of is the bare bones of what you need to know to run those containers on a system like Frontera.
Joe?
Yes.
We have a question from Slack. So what about performance of the app in a container? My laptop might have MKL, Intel compilers, and one API libs. Is there a point where it's not okay for me to expect to run my GNU compiled default ops container code at scale on an HPC system?
In our experience, scaling and performance are extremely good. So there's a little bit of overhead at the beginning of some jobs to, for example, build that CIF image, which is a one-time cost. You can pretty much ignore that. But actually the executable running, we generally don't see any performance loss. And if we do, it's in the very few percent. And team members of ours have run these codes at scale across all 8,000 nodes of Frontera, which is several 100,000 cores without performance loss. So we're not super worried about, if you have an x86-64 compiled executable that you wrote on your laptop and then you're running it on the same architecture, Frontera, I would not worry about performance loss at all. There are some exceptions to that. If you are, say, this is an issue with like the new M1 Mac chips, which are basically ARM architecture. If you have a x86-64 developed container that you pull to your M1 Mac to run there, you'll have to run it sort of in, it's not a hypervisor, but it's some sort of a virtual emulator environment. You'll lose a lot of performance doing that, so sort of how you'll lose performance when you're running a virtual machine. But these are rare cases, for people who are using containerized tools that have been containerized on this architecture, and they're running it on scale in Frontera. I generally would not worry about performance. I see something. The images architecture could not run on the hosts. That is the error I got from M1 to Frontera. Yeah, so this is actually a direction we want to. Oh, you know what? Yeah, Eric,
Yeah, that actually could work. We don't have Frontera set up to. You could set it up so that with QEMU, which is an emulator, so you could have it detect that it's a ARM executable and run it. But you're running under emulation with QEMU, and it's going to be 70 to 80% of the performance of the machine, so it's going to be slower.
Yeah, this is actually. I'm glad you mentioned this, because this is actually like a new issue that we have now that Mac is using M1 chips. Because if you build just by default on your Mac, it's going to use that ARM64 architecture to build, and you push to Docker Hub and it's going to be ARM64 architecture. Then if you go to Frontera, which is x86-64 or AMD 64, and you try to run it, by default, that's just not going to work. Docker has an option for something called a multi-architecture build, where you can build on your M1 Mac for specifically things like Frontera, for those Intel chips and x86-64 instruction sets. But you have there's like flags you have to specify. We're internally talking about sort of that being the next step to this tutorial that we have here, is having some instructions on how to use that. And I think that now that people are in the wild have ARM chips in their laptops, we have to start thinking about that more seriously, because the last 4 years that we've been doing this, everyone's either been on a Mac or Windows or a Linux laptop with an Intel chip, essentially.
Yeah,
Truly,
if you use Docker Desktop for Mac or Windows, that has QEMU built into it. So you could, in theory, on a Mac Docker Desktop, you can pull down an x86 container and run it. It will run under QEMU under emulation. Unfortunately, on Linux, you need to set that up. It's called bin format, BIN FMT. You have to set that up on the Linux system itself to detect that and run different architectures and under emulation. We just haven't set that up.
Yeah, we'll make that a goal of our own, though, internally, to expand the guide that you're currently looking at here. We're going to include information on how to address this specific issue in like a part 4 kind of a thing. We just don't have that yet, but we know how to do it. It's possible. Those guides do exist out on the web, and you can find them. We'll just incorporate it into this and put it all in the same place. Okay, so in the interest of time, I want to go ahead and start this last section. I think this will take 30 minutes or 45 minutes. Are there any other questions before we embark on this last part here?
Nothing in Slack or chat, Joe.
Okay, so here's the thing. The containers we looked at so far, essentially they ran serial processes. It was, a single CPU thread on my laptop. And then when I ran that same Python Py container on Frontera, it just used a single core on a node. Same for cow-say or LOL cow. This executable just uses a single core. It doesn't really exercise the whole power that Frontera has to offer. But it's not the containers doing. It was the code that we were running so far. That code was kind of dinky. It didn't do very much. What we need is a more impressive use case. We need some slightly beefier code that actually can take advantage of, a high performance computing environment and run something a little bit more interesting. One thing to be aware of when you're going down this path, because this is something we didn't have to really consider to this point. When you start to think about creating a container for an HPC cluster, the MPI libraries that are on that cluster begin to matter. Before, what I said was, these codes that we ran, we created a container. That container will just work everywhere. That's kind of true. But now that we're getting into MPI land and actually doing parallelism, we have to be a little bit more thoughtful about how we build our container on our local machine to match the cluster that we plan to have it run on. Several different clusters will have different MPI libraries available. Different MPI libraries are optimized for different cluster interconnects, like the way the nodes are actually connected, or even the specific types of cables that connect the node. So I think MVAPIH2 here is specific for InfiniBand. I could be making that up. So Intel has an MPI library that's optimized for the Intel OmniPath interconnect. And this is really getting into the weeds of MPI libraries, much more than my knowledge holds. So what I tend to do is, at this point, is I think like, these guys at TACC, the guys and girls that work there who develop these or install these modules and tune these libraries to work, they know a lot about it. a lot more about it than I do. So I'm going to rely on their expertise when building Docker images on my laptop. Specifically, I'm going to use TACC's base Docker images. So what does this mean? If I'm going to run an MPI image on Frontera, for example, if I want to run an executable that requires some sort of MPI parallelism, and I want to do that on Frontera, I'm going to go to one of these base images that some expert at TACC has already built and start from there. I think in our python.py, what we did is we started from, we had that from directive. It was from Ubuntu 1804, maybe. Instead of doing that, what I'm going to do is a from, let's say Ubuntu 18 dash and Vapage 2.3 for InfiniBand. Like I can actually use this base image that already has the correct MPI libraries installed inside it, and then just build my software on top of it. And then I know that my software, which uses MPI, will be choosing the right MPI libraries, and I basically just don't even have to worry about it. Anyway, that's a lot of words. It's easier to see what I mean if we just go through the example. And let's see. The one that we're going to use, so in this tutorial, we're going to be using this base image right here. It's TACC Ubuntu 18 IMPI 1907-common. And if you go on Frontera and you list your modules, I believe we chose this because by default, the Intel MPI module is in your path. You can see there's a slight mismatch in version here. The very last decimal goes up by 2 versus this base image, but these are usually just like bug edits, and we probably don't need to worry about that. But in general, I would try to make sure that the MPI major version matches my base image MPI major version as well, just to be on the safe side. Sometimes it might just work without matching, sometimes it won't. And I think what we should try to do is let's run it a couple times with different MPI libraries in our module system and see what happens. Okay. Step one, we need to go back to our laptops and we need to build our first MPI aware container. When Eric did this first part, he had you pull down that Docker file, or I think you actually wrote the Docker file from scratch, and you pulled down the py.py code, and then you use the Docker build command to containerize that whole thing. Let's do that again, but rather than using that original py.py, let's use a new version of py.py that is a little bit more substantial, and it actually uses MPI to do the same thing, but better. So as I normally would, I need to make, a new directory for this work. Let's call it, I'll just call it containers at TACC. What did we call it? That's fine. And the reason I like to make a new directory and navigate into that directory anytime when doing Docker build is because this will basically establish my Docker build context. And so whenever I'm doing a Docker build, it's just going to look at what's in this folder. And that's all I needed to see. And just to remind, in case you didn't catch it, I've got a Frontera tab open over here, but I'm now back on my Mac laptop on the left-hand tab here, because I'm going to do some Docker commands and I'm doing them locally on my laptop. And what I want is these two files. And so the way we can download them, I'm going to open them in new tabs here. So dockerfile.mpi is going to be pretty similar to the other Docker file, which installs Python MPI. It's chmod, this looks familiar. You're doing your apt-get update and upgrade and installing Python 3 and all this. Just the main difference is you start with a different base image that, people at TACC have already prepared for you that contains all of the MPI bits that you need. And then this way you don't have to worry about installing the MPI libraries in the container yourself. So I'm going to go ahead and copy this link. This is pretty small. I'm going to copy this link and I'm just going to wget it right on my laptop over here. Make sure that worked. Okay, so I have a Docker file. And the other thing I needed was this code. So this is the same Python script, or at one point it was the same Python script that we used before, but now it's a little bit different. Now this one has MPI for Pi. Do we install? Yeah. Okay, I forgot to mention this, but now we are importing a non-standard library to get this script to actually use MPI. The non-standard library is called MPI for Pi. And that MPI for Pi was not in our original container. You know, we had to install that dependency. This is part of the process. And so whoever wrote this has put the run command right here to install that MPI for Pi dependency. And basically you initialize the MPI stuff here. It takes the same argument. You have to provide it a number at the end. But what it does, then it looks at how many tasks you initialize. Let's say, for example, we have 8 tasks in our MPI universe. And one of those is the rank 0 or sort of the master task. And all of the other ones will, run that same code and then return their result to the master task, their estimate of the value of pi. And then this master will, rank 0 will take the average of all of those and give you a final, value of pi. So it's essentially the same script. We've just made it an MPI aware script. And I need to wget that as well. To pull it down to my local, this is my laptop I'm working on. And I'm going to go ahead and build this. I didn't do this earlier today, so I don't think this is in my Docker cache. I'm not exactly sure how long this will take. It should be pretty quick. It might take 2 or 3 minutes though still. So when I'm doing a Docker build, I need to provide it a tag. My Docker Hub username is WJ Allen. I'm going to call it PyEstimator. I think I already have this repo we just found out, PyEstimator. So I want to give it a new tag at the end, 0.1-MPI makes sense, because this isn't going to overwrite my 0.1 or my 0.2. Just giving it a new tag will put it in a new space. I have to show, where's the Docker build context right here. And one thing that I don't want to miss is by default, what it does is it looks for a file called Docker file in right here, your Docker build context. But if you have a non-standard Docker file name, you actually have to specify the actual name of the Docker file with this -f flag. This is going to wrap around to the next slide, but -f Docker file MPI so that it knows where to find the actual Docker file. And then here's my build context. So I'm going to go ahead and start that build and let it go. I imagine it's probably going to take a couple minutes. First thing it needs to do is pull down this existing image from Docker Hub. This is our new base image that I believe Eric prepared. And then it's going to run apt-get update, apt-get upgrade. It's going to install Python 3 on top of that. And then it's going to install a new dependency, MPI for Pi. And then it's going to copy that Python script into the container at user local bin. This is already in my path, user local bin, so I won't need to edit my environment to put that in my path, but it is going to make it executable so that I can just call it. All right, let's let this go. Now let everyone else run it as well. When this finishes building, the next things we're going to do is we'll look at this container, make sure it looks like how we expect. It has our code in there and everything. And we'll test it locally on my laptop. I'm not sure if this is going to work or not. We're going to see. But, my laptop is just, it's a Mac. What is it? MacBook Pro or something like that. So I think it has probably 4 cores. I should be able to run this on 2 threads, or 2 MPI tasks, 2 MPI ranks to see if it works. And then if I'm satisfied that it's working, I'm going to push it to Docker Hub. Then we'll hop on over to Frontera. I'll Singularity pull it down, and then I'll run it there. But instead of just running on 1 or 2 ranks like I could on my local laptop, on Frontera, I'll be able to use as many as I have available to me. All right, it's building now. Before I push it, I'm going to test it. Okay. So I'm going to come back to that pushing part. Yeah, we do mention that before using allocation hours of TACC, it's a good idea to test locally. It can be kind of challenging, I think, to test locally on your laptop. MPI containers, anyway, they can be a little finicky. I would say that if you want to test it on Frontera instead, that's fine. Just be prepared to have a little bit longer sort of iteration cycle where you have to build it, push it, jump onto Frontera, pull it, test it. That just takes a little bit longer than just building and testing on the laptop. And I would recommend testing it on Frontera in an interactive job rather than trying to just test it by running it across 100 nodes. If you run it on 100 nodes and it doesn't work, that can be a little bit wasteful. So make sure to test it on a single node first. All right, we built it. I don't see any errors. So I'm going to go ahead and assume this worked. I see it in my tray here at the top. Built 59 seconds ago. It's about 2.5 gigabytes. Now this is going to be much bigger than the other PyEstimator container that you have, because this also has all of those MPI bits baked in, all the MPI libraries it needs, which can be kind of big. So what does it look like to test locally? All right, so here's our local test. It starts pretty much the same as when we were testing it before, but instead of just calling PyMPI, you're going to call MPI run -n and then the number of cores that you want to use, PyMPI. So this is the part that's different. We're using the MPI run executable, which is installed inside the container. We'll see if I have MPI run on my laptop. Nope, I don't. So I couldn't test it that way anyway. I'll have to use the copy that's inside the container. Let's try that. Docker run, I use this --rm because after the container exits, when it's done, I want it to clean itself up and just go away. Oh, this is, I suppose I'm doing an interactive test. No, I don't think I need a -it. I don't think I want to do an interactive test right now. And I'm going to do WJ Allen. It's actually, this is the container right here. /PyEstimator :0.1-MPI. And on our guide here, we did this / just to move it to a new line. This is a Linuxy thing. You can have this whole command on one long line. This / is just to clean it up so it looks a little bit nicer on the guide. But this is the command I'm going to try to run. I'm just going to cut and paste it right there. It wraps around, but this is all on one line. Okay, so here's the MPI part coming to light. So this worked. This is nice. What number did I give it? Is that 10 million? So computing 10 million samples on each of the 1 ranks. I only said MPI run -n1. So I'm only saying 1 rank. There's only going to be that what's called rank 0 in the MPI stack. And the estimate it gave was 3.141, pretty close. And it took 3.5 seconds to come to this answer. So what happens if I run the same command? I want to do 10 million random points. But instead of one rank, I'm going to say use 2 ranks. This is going to use 2 cores on my machine now to run this command. And it's going to divide these 10 million random guesses over 2 simultaneous processes and then take the average at the end. And hopefully what we should see is that it now distributes them over 2 ranks. And then this, sampling time is cut in approximately half. So that's our goal here. That's what we're looking for. Yes. So that's pretty good. So it trimmed it down to 1.8 seconds. And the final estimate was such. So in theory, I could do 20 million guesses in about the same time it took me to do 10 million on 1 rank. It'll give me about 20 million on 2 ranks. So now if you think about Frontera and I have hundreds of thousands of cores, now I have the power to get a closer and closer estimate of pi in the same amount of time by just scaling to more and more cores. And so that, this is why we're using MPI. So I'm satisfied this is working. I'm pretty happy with this. I better push it. Docker push pi estimator 0.1 MPI. So I'm pushing that up to Docker Hub because now I'm ready to go ahead and use that on Frontera. And this one's like a 2.5 gigabyte image. So this can actually this can be a little bit clunky and take a little bit to push. I am on a wired connection right now, so it shouldn't be too bad. It might take a minute. So I'll hop over to Docker Hub. All right, that was pretty quick. It looks like it actually borrowed some of the assets from my base image too, so it didn't have to push that whole 2.5 gigabytes, which is nice. Pretty smart. Okay, so on Docker Hub, I do see it now. Perfect. So now I'm ready to continue with my cycle. I jump on over to Frontera and, oh, yeah. So remember, I can't do a Singularity pull on the login node. I first have to get onto a compute node. And so what I'm going to do, let's just do an IDEV session real quick for 30 minutes or something. Should work. Yes, use the reservation. I just started up an IDEV session. And we'll go back to the guide as well. Oh, yeah, I guess you could just use this command. You can copy and paste it if you like. Oh, you're right. I did this poorly. I made a bad choice. When you're starting an IDEV session, depending on how you have IDEV configured, if you've done nothing to configure it, it might just work. But what you want to make sure you do is instantiate multiple tasks with this little n8 or little n16 or something like that when you start the IDEV session. Because when you're running MPI jobs, specifically when you're running MPI jobs on our compute nodes, when the job starts or is created to begin with, it needs to know how many MPI tasks you're planning on using at that point. You can't decide to use more MPI tasks later in the job if you didn't set the job up correctly. So you have to set it up so that there's more than one task per node to begin with. So this command will set it up for you so that there's at least 8 tasks on your node. And then when you're on the node, you can module load Singularity. And it's actually called TACC Singularity is the name of the module. And then in this case, we say CD to scratch. We do this because generally it's good practice to run jobs out of scratch and so that you don't fill up your home quota. But if you're already on work, for example, I was already in this work folder, this is fine too. This should be okay. And this is okay for kind of lightweight jobs that don't have a lot of file read-write operations. generally jobs that have a lot more read-write operations or has lots of little files associated, you're going to want to run those on Scratch anyway to get better performance. But what I'm going to do is I'm going to use Singularity pull. Now, this is from Docker Hub, so I need to specify the Docker URI, my Docker Hub username, the name of that repository, and the tag from within, which was your one MPI like this. Yeah, that looks right. So let's see how long this takes to pull. I believe I pulled one earlier today with, it looks like the same, probably from the same base image. So a lot of it already existed. This was probably like 2 of those 2.5 gigabytes that it has to pull down. And so this will be a little bit quicker for me than for people who have never pulled it before. Then once it pulls down all those layers, puts them in the Singularity cache, and now it's assembling those layers into a single .cif file, which we'll be able to play around with in just a second here. All right, and now when we actually go to run the MPI aware code that's inside this container, there's an important difference between how we do it on the cluster versus how we do it on our laptops. So on our laptops, if you remember, my command looked like this. I did a Docker run, and then the command I ran inside the container started with MPI run, and then my code. When I'm on the cluster now, I'm going to do it differently. I'm actually taking this MPI run part out, and I'm going to put it in front of the entire thing. So I'm taking this MPI run part out, putting it all the way in the front of the command. On our cluster, we have a modified version of MPI run called IB run, which we ask people to use. But what essentially I've done is that command on Docker on my laptop was right here, the MPI run part, and I'm moving it all the way to the front. And I don't know if I have a good explanation of the why that we do this, but what I don't want to start up a single Singularity process and have it try to spawn a bunch of MPI ranks. What I want to do instead is use MPI run, or in this case, IB run, to create all of the Singularity-based ranks that are then able to communicate with each other. So it's like kind of a minor distinction. And if you just kind of remember that this is what it looks like, it's not too hard to get it right. But this is just how we recommend people do it on our clusters for the best performance. So I'm going to go ahead and try and run this command. IB run works the same as MPI run. If I want to just do one rank, this would be a sequential or a serial run of my code. And the executable looks like Singularity run, the name of the CIF file, which is here, PyEstimator. PyEstimator is 0.1 MPI.cif. And then the command that I want to run inside that container is like this: PyMPI followed by some large number. PyMPI.py followed by, let's say, 10 million again. Let's see how this does. Aha. Now, this is a very nice error to see. So this is actually one of the scarier looking errors that we'll usually get. Error in system call pthread mutex destroy device or resource busy. I see some sort of an error in source MPI init thread. Fatal error. This sounds very dire. P MPI init thread, other MPI error stack. This is a very dire looking error, kind of scary looking. And the reason almost always is that the version of MPI that I have loaded right now in the cluster does not match the version of MPI that I had inside my container, which I find a little concerning because I did this earlier and I didn't get this error. But let me check my environment. And in fact, I do have IMPI loaded here. So it makes me wonder, what did that Docker file actually have? Oh yeah, this was IMPI 1907. So I think something kind of fishy is going on. What I'm going to try to do is switch out the version of IMPI that I have to something else. Let's try this. And see if that gives me a better result. So in our module system, we have a few different versions available. So I'm going to load the exact correct version, which seems like it's a good idea, but I don't think this is going to work when I try to run my Singularity command. I'm kind of skeptical about it. Let's try it. Okay, so one other thing I'm going to try before I go to the professional help is going to be, I kind of have a sneaking suspicion that if I load a completely different library like MVAPage2 GDR, okay. What I've done is I've loaded a completely different library. I'm going to try running this one more time and see what happens. Okay. This is kind of concerning because it works, but I didn't think it was supposed to work. So let's try and debug this. In my container, I used IMPI 1907 as my base. And then I pulled it. So when I did this earlier today, I think I did use an MVAPage base.
Is it possible that that CIF file is your MVAPage based?
That's the thing. I think it might have. So when I did this earlier today, so if anyone is following along and they doing this for the first time and it worked with the IMPI module, please do let me know in Zoom chat. Just mention that it worked. But I suspect, see this part here? I did this earlier today and I'm pretty sure the base that I had in it was MVAPage. And I switched to IMPI for this live tutorial because this was what was already in the guide. So I'm wondering if something in my cache was futzing around with it. But suffice to say, we know that when we see this sort of scary looking error, this generally has to do with a mismatch in the MPI version inside your container and outside the container. But for some reason, MVAPage2 is kind of friendly. MVAPage2 likes this. So for now, I'm going to look into this more and make sure we know exactly what you need to be doing in the guides. But one of these libraries is certainly going to work. And so let's just stick with MVAPage and we'll stick with that and see if it actually lets us do this parallel part, because we only ran one task. And let me see if it can give me, if it'll let me do more. So if I want to do, instead of just one task, if I want to do all 16 tasks, or if I just omit -n, it'll do all of the tasks available to it, but I'll put -n16 and let's see if this is compatible and it works. Yeah, interesting. So let's think back to my laptop. It took about 3.5 seconds to run 10,000 iterations of this code. to arrive at some answer on one rank. And then when we get on Frontera, it only took 0.4 seconds to run 10 million iterations over, let's see, 16 ranks, which, you know, it really cuts the time down that's required to run my code, which is great. And so in theory, I guess I could do like 16 million in around the same time as I can do 10 million on one corner of my laptop. Of course, with MPI, there is a little bit of overhead. It has to get all the answers and put them back together at the end. And it waits for any of the ranks if they're a little bit slow. But if this is close to 3.5 seconds, that means the scaling is extremely good. So this is 6.4 seconds, which for spinning up this is a little bit of one-time cost overhead at the beginning for spinning up the task. That's actually very good scaling. So I suspect if my task were actually much longer, the scaling would look much flatter, which would be nice. Much more linear, that is. Okay. So use IB run on the hosts. For some reason, yeah, another thing, let me try one thing real quick. I'm going to go back to IMPI. Instead of IB run, I'm going to use srun or something like this. This is another, just going to try something real quick. Oh, that just made it look even more dire. Okay, well, Eric, if you do see the issue with this specific container, I'd be happy to know. We'll post it in the chat at some point once we figure this out. But yeah, these MPI libraries can be a little bit finicky. And so far, we haven't found one that we weren't able to get working eventually. But just know that there are caveats for this. All right. Now, this was an interactive test, and I'm going to do one more quick example to finish off this MPI stuff before moving on to the GPU section. What does this same thing look like if you're submitting it in a batch job? So what I did was I logged out. Now I am back on a Frontera login node. I'm still in this same directory. And here's my CIF file. What I want to do is let's edit this pi.slurm. I'm just going to make a copy of it. You know what? Instead, I'm just going to copy and paste what's on the user guide here. So all of these contents into a new file. And let's use the RTX-Q. We can use actually, if you want, you can use like 4 nodes. 4 times 16 is 64 processes, and see how this goes. And 10 minutes should be more than enough time. Module load TACC Singularity. This is the kind of tricky part. We also want to module load and VAPIC to GDR, apparently. And we don't need a CD to scratch because we want to just run it in this directory we're currently in. IB run without any flag right here. We'll just use all of the tasks available to it. And I want to run that CIF file. This is the name of the executable. And 1, 2, 3, 4, 5, 6. Instead of 10 million, let's do something slightly more impressive. Let's do like 1 billion. And I'm going to give that. That's too much. Because I want these jobs to finish pretty quickly. I'll do 100 million, that's fine. Okay. And so once you've prepared your Slurm script, you just have to S-batch it. And then I need to specify -A because I have multiple allocations. And hopefully we'll see if that works. Okay, while that runs, let's see what other pins we can push here. Good job. Yeah, once it's done, it should. Oh, you know what I did wrong? never mind, I did it right. I thought I forgot to change the dash big N. So I did 4 and 64. All right, so yeah, we'll just let that run. We'll check on it a little bit and see how it went. Oh, it's already done. And I think this is my output here. Okay, yeah, give me the fatal error. I'm going to try that one more time and not load MVAPage 2 GGR. I'm going to try this with that standard version of MPI that we had before. Let me try this job one more time. I'll submit it. So, yeah, it's nice to be able to work through some of these errors because, you know, a lot of the researchers that are using these codes on our resources are running into these same things. And I was very flippantly saying that, you know, Docker containers are a magic solution to everything at the beginning, which in part is true, but that's not to say that they aren't without their challenges or limitations. And in our experience, Eric and I, in supporting containers, MPI has definitely been a little bit of a difficulty, especially as we juggle different MPI libraries on different machines. And generally, we are able to figure it out eventually. So the trick is if you're trying to run an MPI aware container and you're running into these same kinds of problems that we are, submit a ticket and we'll help you work through them. But yeah, the general rule of thumb is that if the MPI version within the container matches what's on the host system, it should generally just work. But, you know, evidently it doesn't. Okay, let's try this one more time. This file size looks suspiciously close to my previous file size, so I'm a little bit worried that I've got lots more of the same errors. Yeah, I'll figure this out in a little bit. But let's move on to the GPU part so we can get that working. And then we should end in about 15 minutes from now, I think. But we'll stay on to help anyone else with questions or to get this working or work one-on-one with you as well. Okay. So GPU, this is the last part. Just like the MPI libraries, the base images that we provide for you, we've also prepared some base images to support general purpose GPU code running on TACC resources. And where the caveat for MPI libraries is that the libraries should match. On GPU, what you need to do, the thing that you need to make sure of is that the NVIDIA driver on your host system on Frontera supports the version of CUDA that's inside your base image. So for example, if we go over to Frontera and we look for what CUDA is available, we'll see CUDA version 10, 10.1, 11, 11.3. So the NVIDIA driver, and I'm pretty confident about this, but the NVIDIA driver currently installed on Frontera should probably support anything as new as 11.3, and it probably should be retroactive up to about 10.0. So I think base images with versions of CUDA between about 10.0 and 11.3 should all work on Frontera. And I think we're actually going to try one of those right now. So I'll go to this list and we'll see that Frontera, it's actually got the check marks to help you specify if you want to use like a pre-baked image with TensorFlow already installed that's compatible with CUDA 10. We have this here, or here's TensorFlow 2.4 with CUDA 10. And what I think we want to do, oh, you know what we do want to do is let's hop on to a compute node in an interactive session like this, and let's pull a base image and just sort of see how you can get that image to recognize that there are GPUs available on this machine. So to do that, I'm going to IDEV, let's say a 60-minute session. This is much longer than we need, to the RTX queue, which is our GPU queue. And once this job begins, make sure you load Singularity if you haven't already. And I'm going to, it's called TACC Singularity. I'm going to Singularity pull. And so this Singularity pull command is not using the GPU. This is just a standard CPU-based Singularity pull command. And I'm going to pull the stock NVIDIA Cafe image. So as you kind of debate and decide what image you want to pull, if you want to build on top of one of the images that we provide, or if you want to go to Docker Hub, you might need to go through their documentation to see what versions of CUDA might be included inside this image and double check that they're compatible with the driver on the host system that you're planning to use that image on. And if you can find the Docker file for this base image, that's usually the place to start and look through there to see what version of CUDA they install. On these RTX nodes that I'm currently running on, there are 2 Intel chips with 8 cores each, so 16 CPU cores. Plus, there are 4 RTX GPUs, and the RTX GPUs are indexed, so they're referred to as number 0, number 1, number 2, number 3. Those are how we refer to the 4 of them. If I want to run a command with Singularity, by default, it's just going to go to one of those Intel CPUs. It's going to go down that lane. So if I do like a Singularity exec, the name of the thing I just pulled, and then this was like a default command from inside there might be Cafe. But instead of going down just one of the Intel CPUs, if I want to make this whole command aware of a GPU, I have to give it a little bit more information. So I have to specify --NV. I suspect this has to do something with NVIDIA, but I'm making this container and this command aware that I'm about to start working with GPUs. And this actually Cafe device query command is going to query the first GPU on the system, GPU index at number 0, and provide some information about it, like what kind of GPU is it, for example. So I'm doing a Cafe device query GPU 0. And this is showing me some information about that specific GPU. You can do GPU 1 as well. It should be pretty much identical. And this is telling us that Cafe is able to see our GPUs, which is good. It didn't like this one for some reason. It's hanging, so I'm going to pause it. So --NV makes it aware of GPUs. Let's see what else. CUDA 10 on the host system, CUDA 10 internally. Here's a more exciting test. The latest version of TensorFlow can be benchmarked. Rather than run this test, I'm going to skip ahead. This is a nice one. I'm not 100% sure how long this command takes to run. Something on my node really doesn't like this, but what I want to get through is this very last part where we're actually building a GPU aware container on our laptops. So this again is really important to go through, I think, the sort of entire Docker build workflow that we go through. We start on our laptops. We like to build in Docker. We like to push to Docker Hub, then we jump onto Frontera, Singularity, pull those containers down, and Singularity run them from there. And so, I don't have NVIDIA GPUs coming out of my laptop. So, how does this workflow look when I'm building on a system that might not really support the code I'm trying to run? And here's a good example of that. So there is a natural language processing classification tool that uses something called BERT, transformer model. Works within PyTorch. And what we're going to do is let's clone this repository right here. We can git clone it. And that's going to give us a few files filled with data, an actual classifier Python script here, and then the Docker file, which contains a TACC base image that we've prepared for Frontera. Plus, it will install the dependencies and copy the data into the data as well as the Python script into the container so that we can run it on Frontera. Let's see, let's go back. So in order to do all this, step one, the speediest way, rather than trying to download all of these files individually, is here on your laptop. Am I on my laptop? Yeah, so this is on my laptop. I'm going to make a new folder called actually, instead of making my own folder, I can just clone this repository right here. And this repository essentially just has these files in it, and I think a README as well. Once I clone that repository, the Docker file is already set up for me. Here's that script. Here's the data that I need. And I just want to double check that this Docker file is what I expect. Yeah, so this Docker file is going to use a base image that I'm comfortable with. It has CUDA 10. So I know that should work on Frontera. The Frontera NVIDIA driver supports CUDA 10. And I'm going to conda install a couple dependencies, transformers, Seaborn, torch text, and then this Docker file copies all those test training validation files into the container, as well as the script that we actually want to run. And then it makes that script executable so that we can just call it. So once I'm prepared with this, you as developers, if you prepare your repositories or Git repositories carefully, like this one that Eric's prepared, it makes it really easy for people to clone your repository and build containers of your stuff if they want to. So if they want to modify this classifier a little bit, change some parameters in there, and then rebuild it, they have all the tools that they need to do that right in front of them, which is really nice to have. So what would it look like to build this? It'd be a Docker build commands. The tag I want to give it, I think I want to call it like BERT classifier. Let's call it like 0.1. Actually, I believe the command's probably going to be right here. Yeah. And just make sure to replace your Docker Hub username at the beginning here. And I have to specify the build context. Don't forget this single dot at the very end of the line. If you're running this for the first time, I think it took me about 6 or 7 minutes to run this. And the main parts that take a while are those conda installs. These can be they can take a little bit. So, give yourself a little bit of time. Since I already ran it, it should use the cached version. It's going to be a little bit quicker for me. Yeah, so sure enough, it's using the cached versions of these commands that I previously did. And if I list my images with Docker images on my local laptop, I do see that I built this BERT classifier 4 hours ago. It's a little bit big, actually. So my next step is I need to push this up to Docker Hub so that I can pull it on the cluster as well. So I'm going to go ahead and do that. Docker push WG-Allen BERT classifier. Like so. And I already pushed it too, so that was much quicker than it would be if you hadn't already pushed it. Yeah, being on a wired connection definitely helps with large pushes. They can be tedious. So while you all, if you're following along, while you build and while you push, if you think back to our suggested workflow, it'd be good to be able to test this locally before I go and commit my energy to Frontera and get IDEV sessions and test it up there. It'll just help and speed up my build process or my sort of development cycle if I'm testing it locally on my laptop before committing to Frontera. So how do I test locally? As I mentioned, I don't have a bunch of beefy GPUs coming out of my computer. So what I want to do is, one thing we can do here is actually just, issue that bird classifier help text. This is one way to test without actually running the GPU bits of the code. At least I'm confirming. Control C that. It's trying to pull Erica's up. I should use my username here, WJ Allen. I don't think I want interactive either. So I'm running my local copy of the container, just gonna produce the help text, and I can confirm, okay, well, bird classifier.py, if I do a -h, what it does is, well, it's going to try to do all the imports at the top of that Python script. So I at least know those work because I didn't, get an error. So I'm pretty confident that at least the dependencies are all resolved. Whether or not this is working on GPU yet remains to be seen, but I really need to go into my development environment on Frontera to test that. There is a way to offload this to a CPU with this -D CPU at the end. It's just saying you can choose to run on a CPU device, which is not the default. I don't need to do that on my local laptop. That will take a while, so I'm going to ignore that. But this would be a way to just test that the code is working. What I really want to know, though, is whether this is working on GPUs. So let's try it. I'm going to, I pushed it already. What's next is I go on over to Frontera. It looks like I'm already on a GPU node, so I don't have to IDEV into it. And I should already have Singularity loaded, which I do. So I can go straight ahead to Singularity pulling my bird classifier from Docker Hub. Actually, let me see where I am first. Containers at TACC. Well, I feel comfortable stacking multiple containers in the same directory. I think that's fine. Singularity pull from Docker Hub. WJ Allen is my username. Bird classifier 0.0.1. That looks right. And I believe, I don't think I tested this on Frontera today, so I think this is the first time it's pulling it to Frontera. And this image is definitely on the larger image size. It was up in like the 7 GB range, I believe. So this kind of gives you a demonstration of how long it takes to pull large images that you have to budget for if you choose to pull it at the beginning of the job. And it's likely going to take another 2 to 3 minutes here. But once that's pulled, we've reached the very end of the guide. We're going to try to run it. And don't forget, when you do Singularity exec, you just have to specify this --NV flag so that it is aware of and actually uses the GPUs that are on this card, on this node. Okay, so it's pulled all of the different layers down into the local Singularity cache, which is on my Scratch file system. Right now, it looks like it's getting ready to assemble those layers into one .cif file. So this should take about another minute, I think. Are there any other questions? We've had a lot of really good questions today. In my experience, most of the users that are using containers on TACC systems are not doing CUDA aware or MPI containers. Most of the jobs that we see come through are slightly less sophisticated. They're just, single serial processes. That's, most of what I do as well. And those ones feel to me like they're almost always bulletproof and they just work most of the time. GPU aware containers and MPI aware containers are definitely a little bit more finicky and they have challenges, but these are one of those things where as soon as you figure out the Docker file and sort of the libraries you need and the run command, then it's solid from there and it just sort of works. And again, as those serial unsophisticated containers, we find that the MPI and the NVIDIA containers are really extremely low overhead. So the applications that are containerized within run at essentially, no overhead. Save the overhead of downloading the container itself. But this, in the end, much easier than trying to install the software on Frontera.
Joe, it seems like they're undoing some of the advantage of the not having to worry about version compatibility and so on with these MPI.
Oh yeah, for sure. I completely agree. And that is one of the, I think, challenges. I don't want to say it's like a limitation of containers because containers provide so much benefit. However, that is definitely one of the things when you're doing MPI containers, for example, that you have to think about and be aware of and account for. It's definitely an extra step, but it helps save you from, I don't also have to juggle the to run my Python MPI container. I do have to get the MPI library right, which is a step. But I don't have to worry about like the PyMPI dependencies, which may not be available on Frontera. And, in our toy example, it had very few dependencies and it was really easy, sort of straightforward thing. But some of the codes we work with, so for example, there's this code for cryo-EM called Eman, which has this really disgusting list of dependencies. It's an MPI aware code. And all those dependencies gain and working on Frontera is a massive headache. But if I can containerize the whole thing and only have to worry about making sure the MPI matches, it's much less of a headache.
Yeah, I can see that for Python in particular, where you can have so many dependencies.
So it looks like that pulled. I'm going to go ahead and try and run it and see what it does.
Hey, Joe, when you run this, you probably want to redirect standard error to a file. Otherwise, it's the warnings are very wordy. You're going to obscure all the progress messages if you don't do that.
Okay.
And yes, and while like MPI and GPU containers are a little leaky and that they do take into account what's on the host, you're still getting all the other benefits of containers, all the dependency management and stuff like that. So it's still a win.
I agree. Do I want to direct standard output to a file, or can I just let that go to screen?
Just standard error should be fine.
Okay, let's just see what this does. I'm nervous. It's so quiet.
It takes a while to warm up. It's doing all the training and stuff. There you go.
Right, because the model it generates is based on CSV files that are inside the container, right? Yeah. Nothing to have locally.
And if you want to prove that it's actually running on GPUs, you might want to SSH into that node and run NVIDIA SMI if you want to prove that it's actually running on GPU.
I feel like by the time I got another shell into here, it might be already done, but let's go ahead and try it.
You still got a little while to go, so.
Okay, so I'll log into Frontera in this other terminal. And I can look at my jobs with SQ. I see this is the node I'm on. So I can SSH that. No, it's going. So now I'm on the node. My job is presumably running. And this NVIDIA SMI command will show me that.
But right now, it still hasn't hit the GPU yet, so you're still okay. Now try it. Try it again. Try NVIDIA SMI again.
Am I going to miss it?
You got it. Now you got it. Now it's on the GPU.
So yeah, now it is definitely running on the GPU. So this is good confirmation that it's actually using the GPU, which is nice. I suspect if I omitted --NV, it might give an error because by default the hardware directs to is GPU. But if I did omitted NV and added the -D CPU at the end, it would just stick on the CPU the whole way, would be my guess. All right, so here's a nice thing that's happening. The data that we had to train this model was all just inside the container. And as I'm looking at it, model save to.model.pt, I suspect this means that it's writing a lot of files right here to my local disk in this folder, which I think I'm on, work. So this is nice that you don't have to worry about mounting some sort of an output folder inside the container and having it right to that output folder so that you can capture the results on the outside. That's essentially what you need to do with Docker. Here, if you're just working on home or work or scratch, all of the data is just right there. Okay, yeah, it looks like that worked, whatever all this means. And the GPU should be quiet now. So that's actually the end of our training here. I think we've got some next steps on our side. You know, Eric and I and John are always working on this documentation. We're definitely going to add a part 4 at some point for something like multi-architecture builds or sort of more advanced uses of Docker. And if you all have any questions or not even just about the material we went over today, but if you're working on something else that you'd like to just talk to us about and maybe get some advice on building Docker images or running containers, we'll be here until you all sign off, until 4 p.m. at least. And thank everybody so much for their attention. I don't know if John or if Eric, if you had any closing thoughts or comments.
Yeah, not other than just thanking everybody for sticking around all day, and I hope the information was useful.
Is John back on? Yeah, I see him.
Just let me know when you're ready to pause the recording.
You could probably stop the recording now, and then we'll